So hello everyone, welcome to another particular course. So in this particular course, we are talking about reagent chemistry, and this particular chapter is very important for exam point of view, as well as if you want to learn organic chemistry, then you have to learn reagent chemistry in details, because the reagent chemistry, I believe that it will be the key backbone of organic synthesis part. Okay, so I have briefly categorized this particular reagent chemistry with this particular four different segments. So in our first segment, we are talking about the basics that you have to know about the particular before starting the reagent chemistry. So first we are talking about the introduction of reagent, like what is reagent and how the reagent is different with catalysis. Okay, then we'll learn about the oxidation and reduction. What is mean by oxidation and reduction in terms of organic chemistry point of view, as well as we are discussing about the how to calculate oxidation and reduction of a particular group or particular center. Okay, like in the case of aldehyde acid, what is the oxidation number of the carbon center? We'll discuss about this. And later we are talking about the selectivity of organic reaction, because learning selectivity is very important, because some of the reagents are there which actually works with certain functional group, keeping the other functional group intact. So you have to learn about the various stereochemistry associated with the reagent chemistry part, like regioselectivity, chemoselectivity. So with this, we have to end the basics. Next, we are talking about the reduction part first. Reduction part first, we are talking about the different reducing agents, such as the nucleophilic reagent, nucleophilic reducing agent, and the electrophilic reducing agent. Then we are talking about the solvated metal ion mediated reduction, and then talking about the hydrogenation. And till here, I think it will be enough for the examination that we are targeting for, like IIT JAM, CSIR NET, and GATE examination. Okay, we have end our discussion regarding reduction here. Then we are move on to the organometallic reagents. Organometallic reagent, mainly we are limited with the grignard reagent, Gilman reagents, and organolithium based reagents. Then we actually shifted our focus to the oxidation. Oxidation, there is a mainly four broad classification is there. One is the chromium based reagents, one is the manganese based reagent, one is the DMSO based reagent, and there are some organic reagents are there which actually used in the oxidation, such as hypervalent iodine mediated oxidating agent. Then we can say about the tempo mediated oxidation. So this is the organic based reagent. So with this we have to wrap up our reagent chemistry classes, and it will be a very vast lecture, like so many lectures are there. So have faith, we will complete with accordingly. Okay, so with this we have to enter in our first particular lecture, that is the introduction of reagent. First, let us understand that what is the reagent. A reagent is a substance or compound that actually added stoichiometry to a system which cause a chemical reaction to occur. Now, I have highlighted this particular term stoichiometry because this term actually differ a reagent and a catalysis. Okay, so let us understand that what is the basic difference between a reagent and catalysis, because sometimes we often confuse about the reagent, what is the reagent and what is the catalysis. So I hope that this particular comparison will clear out all your doubts. Okay, so difference between reagent and catalysis. First and the foremost difference between a reagent and catalysis is reagent use stoichiometric amount. Like stoichiometric amount means, like if you use your substituent 1 molar or 1 millimolar amount, then your reagent will be either 1 millimole or 0.8 millimole, or a little bit of excess, it is a 1.2 millimole, vice versa. But in the case of catalysis, we use in catalytic amount. Like if your substrate use in a 1 millimolar sorry, use in a 1 millimolar ratio, then your catalysis may be a 0.001 millimolar ratio. So this is the foremost difference between a reagent and a catalysis. Also, there is another important difference between a reagent and catalysis is a reagent completely consumed in a reaction. That means reagent, some part of the reagent will actually attach with the substituent to get our product. That means reagent cannot be recoverable. But in the case of catalysis, what happened that it drives the reaction, or you can say that it drives the kinetics of the reaction. Like it helps to do the reaction with a lower activation energy, or we can say that catalysis will help the reaction to go fast. Maybe sometime in the case of negative catalysis, or the reaction rate will decrease, but the catalysis can alter the reaction rate, but at the end of the reaction catalysis will we can actually recover the particular catalysis from the reaction mixture. Okay, so here also third point, catalysis can alter the reaction rate, but reagent doesn't have any role in reaction kinetics that I already discussed. And reagent actively participate in the catalysis, where catalysis partially participate in the reaction. When I will teach about the asymmetric synthesis part, there you can find that some kind of bifunctional catalysis or some kind of proline mediated catalysis, they are actually help to stabilize the transition state by doing some kind of hydrogen bonding or some kind of other non van der Waals interaction or some kind of other interaction. It can stabilize the transition state, and by stabilizing the transition state, what happened that the particular reaction kinetics or the activation energy of moving the reaction towards the product side is goes down, and due to this particular phenomena, the reaction kinetics were altered. Okay, and that's why, and after the stabilizing the energy of the particular transition state, the catalysis removed the particular system, and we got our product back. So catalysis doesn't present in the final product. It will actually attach the particular substrate in situ manner, and then it will remove after his job is done, and the job of the catalysis is simply alter the reaction kinetics. So I hope that this uh, will be enough for understanding that what is the difference between a reagent and catalysis. Now we move our next segment, that is the oxidation and reduction of functional group. So inorganic term, we can say that the broader definition of oxidation and reduction are referred to the loss of electron and gain of electron. Like oxidation suggests that your compound had lost some kind of electrons, some number of electrons, and the reduction specifies that your compound gained some kind of electron from either external medium or by doing some kind of reaction. Okay, or we can say that oxidation leads to the increase in oxidation number, and in the case of reduction, it decrease the oxidation number. Now it will be a little bit confusion about the oxidation and oxidation number, but we can understand that if a particular compound lose some kind of electron, then we can say this is oxidized or oxidation happens, and if any compound gains some kind of electrons, then we can say the reduction happens. Now when it will be in the organic chemistry point of view, it is a little bit of change. Like in the case of organic chemistry, if any compound has gained oxygen, then we can say it is an oxidation, and also if the compound lose hydrogen, then it is also called an oxidation. Okay, so in practice, a series of functional group has been quantitatively identified in the order of increasing oxidation strength. So thus oxidation is referred to as the conversion of one functional group higher in the sequence of another lower functional group. Okay, so this particular segment I will explain with the example, but give me some more time to discuss about the reduction part in terms of organic chemistry point of view. Okay, so similarly in organic chemistry, as the oxidation suggests the gain of oxygen, so the reduction will be the vice versa. That means the reduction suggests the loss of oxygen or gain of hydrogen is often referred as reduction. Okay, and alternatively, reduction is referred to as the conversion of one functional group lower in the sequence of another higher functional group. Now let us understand with this simple yet important example. Now here you can see this is our aldehyde. Okay. Now if we go this pathway, so it will generate an acid. That means this particular carbon is getting one oxygen. That means this particular aldehyde moiety will gain one oxygen. That means it will be oxidation. Similarly, if we go this way or backward pathway, like this particular oxygen is there, but here it is present in a double bond. Now here this particular oxygen present in a single bond, and also there is a only one hydrogen is there, but now here is a two hydrogen is there. That means this particular aldehyde, while going via this backward pathway, will gain one particular hydrogen. That means this is the reduction takes place. Now we can talk about the oxidation numbers. Like here in this particular carbon, if we calculate the oxidation number, this is +1. Now, how to calculate oxidation number, we'll learn in this particular lecture, but a little later. Okay. And here in the case of carboxylic acid part, the oxidation number of this particular carbon, this is center carbon, is +3. Similarly, here this oxidation number of this particular center carbon is -1. So here you can see the trend. Find that in the case of aldehyde, the oxidation number of this particular carbon is +1. Similarly, if we go via backward, in the case of alcohol, the oxidation number is +1, -1. And in the case of carboxylic acid, the oxidation number is +3. Now you can understand this important phenomena here. Now this particular aldehyde, while going this particular pathway, okay, will gain 2 electron. Okay. Now while it will gain 2 electron, then its oxidation number goes +1 to -1. Okay. And similarly, while moving this particular way, like alcohol to aldehyde, it will lose 2 electron. Okay, so that means it is initially -1, then it is lose 2 electron. That means the increase in oxidation number to get the +1. Okay, similarly, if we see here that in this particular aldehyde, it is +1 to +3. That means number of increase in oxidation state is +2. That means this particular aldehyde will lose 2 electron, okay, to getting this particular structure. That means it is oxidation takes place. Similarly, if we go via backward from carboxylic acid to aldehyde, there will be a number oxidation number changes 2, but here carboxylic acid gain 2 electron, and due to the gaining of 2 electron, the oxidation number of +3 is now reduced to +1. That means we are actually proved the basic condition of oxidation and reduction. Like oxidation is the mean loss of electron and the reduction means gain of electron. I hope this will be clear for you. Now we are talking about a very interesting thing, that is the how to determine the oxidation state. Now first we have to understand that what is the oxidation number of oxidation state. The oxidation number or oxidation state of an atom is the charge that would exist on the atom if the bonding was completely ionic. Like here we are discuss about the oxidation number. Like if this particular bonds are completely ionic, then we can say that this particular carbon having the +3 oxidation number. Okay. And this will be very much important in terms of reagent chemistry pattern. Not only reagent chemistry, like in case of any kind of organic transformation, or we can precisely say that in case of redox transformation, the determination of oxidation state is very important. Okay. Now how to determine the oxidation number of any organic compound? Okay, there is certain rules are there. Like the first rule suggests the oxidation state of uncombined element is 0. That means when you are seeing the Cl2, Br2, H2, this type of compound are actually uncombined. So the oxidation number is 0. Okay. The second rule suggests that the sum of the oxidation state of all the atom or ion in neutral compound is 0, and sum of oxidation state of all the atoms of ion in the ionic compound is equal to the charge of the ion. This will be very important. And the third rule that is also very significant in the determination of oxidation state, that is, between a bond, the most electronegative atom is often assigned a negative oxidation state, and the less electronegative atom is assigned to a positive oxidation state. And if the particular compound having the same atom which having the same electron possess the same electron negativity, then this type of atoms have no effect to determine oxidation state. We'll explain it in the example part in the next part. Okay. So before that, we have to understand that another thing, that some of the element, when we are calculating oxidation state of a particular organic compound, we have to remember that some of the elements has shown the same oxidation state in their compounds. Like when the particular organic compound having any kind of group 1 element, then it will show always +1 oxidation state. Similarly, when the compound is in a group 2 element, they will show always +2 oxidation state. Now in the case of oxygen, like if your organic compound contains oxygen, it shows usually -2, not +2, usually show -2. But in the case of peroxide, superoxide and F2O, it will show different oxidation states. Now if your compound have hydrogen, then it will usually show +1, but in the case of metal hydrides, it will show -1 oxidation state. Fluorine is the highest electronegative atom, so it will always shows -1 oxidation state. Chlorine is usually -1 shown, but when it will combine with the compound with oxygen and fluorine, which is the higher electronegative than fluorine, then it will show variable oxidation states. Okay, so now we do some kind of practical approach to understand or determine the oxidation state of certain compound. So here let us do some hands-on example to determine the oxidation state of the following compound. This is the mark sheet. So first we are talking about this. So this is CH3 COOH. So we have to determine the oxidation state of this particular center. So let us assume that the oxidation state is X of this particular carbon. Okay. So now we have to determine, see, this also carbon, this also carbon. So that means this particular carbon will doesn't show any effect to determine the oxidation state of this particular center. So the oxidation center of this particular carbon will solely determined by this particular oxygen and the OH group. Okay. So this oxygen will contribute -2. Okay. This particular oxygen will contribute -2, but since one hydrogen is attached with this particular oxygen in direct fashion, so due to electronegativity difference, this particular hydrogen will also show the +1. And from our rules of determining oxidation state, we know that since it is a neutral compound, that means the sum of the oxidation state is equal to 0, since it is a neutral. So let us determine, like for the carbon it is X, for this particular oxygen it will -2, this oxygen will contribute also -2, and this particular hydrogen will contribute +1, equal to 0 as per the rules. So that means the X will be +3. So the oxidation state of this particular carbon in carboxylic acid is +3. Similarly, let us understand to determine the oxidation state of this ketone. Uh, this will be easy. Okay. So what happened that these two particular carbon, this also carbon, so they are similar atom. Although you might get confusion that why this particular hydrogen not even considered. This hydrogen even considered if this is not carbon, this is nitrogen. Okay, because then this bond have a electronegativity difference due to this particular different atoms having different electronegativity. Since these both are carbon, so these carbons are not actually participate to or influence this particular influence or participate in this particular determining the oxidation state of this particular carbon. Okay, so this particular oxygen center will contribute -2, and we are assume that this have X. So since it is a neutral compound, so the count will be 0. So X -2 equal to 0, or X equal to +2 here. So this particular ketone, the oxidation state is +2. Now let's talk about the methanol. OH, H, H, and H. Okay, so here you can see that all the particular carbon atom having the direct bond with different electronegative atoms. So all are actually counted. So as our previous discussion, let us assume that the oxidation state of this particular carbon is X. So all of the hydrogen is contribute +1, +1. This particular oxygen will contribute -2, and since this particular oxygen is directly contact with the hydrogen, so this hydrogen will contribute +1. So X +1 +1 +1 -2 +1 equal to 0, since it is a neutral compound. So the count will be 0. So we just simply calculate here, and we observe that the X will be -2 for the case of methanol. So say that all the time the carbon oxidation state will not be in plus, sometime it will go for a minus also. Now we are talking about this particular ethanol. Methanol is done. Now we are talking about ethanol. So I am just rubbing out this particular carboxylic acid and do the ethanol. So it contains 2 hydrogen, 1 OH, and 1 methyl. Now since it is a carbon-carbon bond, so it will not contribute. So we can easily omit this particular thing, or we can assume that it is 0. Okay, and this will provide +1. This also contribute +1. This -2, and since the oxygen is there, so it will contribute +1. So since this is also a neutral molecule, that means and this is assume X. So X +1 +1 -2 +1 equal to 0, or X will be -1. X will be -1. So with like this, you have to determine the oxidation state of the following compounds. So there is a little homework for you, like determine the oxidation state of these two particular. It is already, you know, the answer in our third or fourth slide. It will be clearly written that the oxidation state of this particular carbon, but you will determine the formaldehyde, and put the answer in the comment section. I will, uh, whoever goes correct, I will give a heart or pin the particular comment. Nucleophilic reagent, electrophilic reagent. So in this particular class, actually we are mainly focusing on the sodium borohydrates. Okay, we will see this type of things in our further discussion in the case of reducing reagents. So the nucleophilic reducing reagent is mostly associated with the sodium borohydrate and their derivatives, lithium borohydrate and their derivatives, zinc borohydrate, lithium aluminium hydrate, red aluminium hydrate, and selectrides. Then we are focusing on the electrophilic reducing agent that provides the BH3 or B2H6, divalH and ALH3, and solvated metal ion based reduction such as Birch reduction. That is a sodium liquid ammonia based reduction. So this is our most content in the case of reducing agent, and after that we will talk about the hydrogenation part later. But in this particular class, we are mainly focused on the sodium borohydrate. Okay. So first we are talking about some information regarding the sodium borohydrate reducing agent. So sodium borohydrate is a moisture sensitive reagent, which is the physical property of the NaBH4 is it is a white to grayish crystalline powder, and this NaBH4 is soluble in water and certain organic solvents. And the sodium borohydrate is used or known for being a mild and selective reducing agent. Like we already discussed about the chemoselectivity, so chemoselectivity has takes important part in this NaBH4 based reduction. Okay, and NaBH the work what actually NaBH4 job? The NaBH4 job is to commonly used to reduce the aldehyde and or ketones to their corresponding alcohols, and it is selective for the carbonyl group reduction and typically doesn't reduce ester, amides or carboxylic acid under standard condition. So first let us understand about what the actually NaBH4 standard condition and what kind of solvent actually we are using in terms of NaBH4 based reduction. Okay, so give us in the next slide. So NaBH4 that the FAQs are there, like the facts of NaBH4. It is a mild and chemoselective reagent. It's actually mainly reduce the carbonyl compound. It is a hydride donor. So basically, if you see the structure of NaBH4, it is something like this. And this particular BH bond actually cleaves during the reaction, which forms a hydride H minus, and this particular H minus actually acts as a nucleophile which attacks to the carbon electrophilic center. Here there is a carbonyl carbon, that is the electrophilic in nature. So this particular hydride will attack in the electrophilic center of the carbonyl compound, that is the carbonyl carbon, to generate the corresponding alcohol. So what kind of solvent actually used with the NaBH4? Like as I discussed in the previous slides, that NaBH4 will actually soluble in certain organic solvents. So usually it is observed that while we are actually dealing with NaBH4 in the case of reducing agent, so methanol or ethanol actually used as a solvent, and this particular solvent have a very unique role in the mechanistic pathway. So we'll discuss in the next slide. Okay, and the reaction condition is very mild. Like usually it will react in the 0 degree temperature, and also we get fruitful yield in the room temperature based reaction also. And NaBH4 doesn't react with protic solvent; it will only react with the aldehyde and ketones. And the final product is alcohol. So here you can see that this is the aldehyde and this is the ketone, which react with the NaBH4 to generate their corresponding alcohol. Now the corresponding alcohol might be primary alcohol or secondary alcohol, and it's depend upon the what the substrate has been reacted with NaBH4. Like if it is react with the aldehyde, then the final product will be the primary alcohol, and if it is react with the ketone, then it will form the secondary alcohol, and this is very obvious. So now let us deep down in the mechanistic pathway of the particular NaBH4 based reduction. So what the mechanism? Mechanism is that this is NaBH4, and as I already discussed, that one of the BH bond getting cleaved, and so generate this particular hydride. Now this hydride will at a acts as a nucleophile, and this particular nucleophile will attack this particular carbonyl carbon, which is electropositive in nature. So what happened that this bond takes place and the remaining O getting O minus, and this particular O minus are actually chelate with the rest BH3 present in the particular reaction medium. Okay, and thus getting stabilized. Now if we look closely here, then the BH3 contains more 3 hydrogen to generate the corresponding hydride. So what happened that this 3 hydrogen will also form hydride, and it will react with another 3 mole of our corresponding carbonyl compound, and to form this kind of gigantic intermediate. So here one point has been noted that if 1 mole of NaBH4 can able to reduce 4 mole of carbonyl compound. NaBH4 contains 4 hydrides, so 1 mole of NaBH4 is actually able to reduce 4 mole of carbonyl compound. Okay, and after generating this type of gigantic intermediate, so what happened that this particular BO bond getting cleaved in presence of solvent, so it is called the solvent quenching, and after solvent quenching we got our this product. Now as I already discussed in our previous slide that the solvent have have interesting role in the case of mechanistic pathway while treating a carbonyl compound with NaBH4. So here you can find here that one of the like in the initial part when the carbonyl compound is there and the product here, so the main difference is that 2 hydrogen is added in this particular uh, reactant, there is the carbonyl compound. So what happened that one of the hydrogen directly comes from the reagent, like here it is a NaBH4, and the other hydrogen is come from the solvent itself. So that we can say that the hydride or the hydrogen connected with the carbonyl carbon, which directly come from the reagent, that is a sodium borohydride, and the hydrogen that actually connected with the oxygen center that come from the solvent. And here we can the a figure that I already discussed in the previous slide, that when NaBH4 react with the aldehyde, then primary alcohol form, and when the NaBH4 react with the ketone, then secondary alcohol form. Okay, so now let us talk about the general trend of NaBH4 based reaction. So NaBH4 usually attack from the less hindered side to avoid steric interaction. As the example here, it is a clean reaction of epoxide opening. So what happened that NaBH4 is actually generating this hydride, that is H minus, and this H minus will actually attack this particular center because it have the possibility to this two center. Now we can say the regioselectivity comes into the picture here, like this center getting lesser hindered over to this particular center. So this particular hydride actually attacks here and the epoxide opening takes place to form this type of compound. And usually this type of trend has been observed that when actually NaBH4 used in terms of reduction reaction, then it will try to form attack from the less hindered side. But also there is an ambiguity is there, like under acidic condition hydride attacks observed from more hindered side. Actually this is happening when this particular acidic condition is there, that means the particular medium contains more hydrogen or H plus. So what happened that this particular lone pair from the oxygen is actually conjugate with this particular hydrogen or acidic condition. So this will generate a positive ion and it will follow a loose SN1 mechanism. So what happened that now this particular bond actually mostly swept to this here. So the NaBH4, the hydride will attack here because now this particular center become electrophilic, and since it is a nucleophilic, so simply a electrophilic nucleophilic reaction takes place to form this type of major product, and this follows the loose SN1 pathway. So we'll discuss when we are actually learn about SN1 SN2 reaction, then we'll discuss in brief about the loose SN1 pathway. Okay, simply say that here after generating this type of intermediate, del positive or partial positive charge has been generated here, which attracts the nucleophile more towards it. So irrespective of the corresponding steric hindrance, the nucleophile will attack here to form this as a major product. Okay, so there is also temperature selectivity of NaBH4. Like if your compound or if your starting material contains both the aldehyde and ketone, so in case of 0 degree temperature or room temperature, in the adequate amount of NaBH4, both groups are getting reduced, like both the ketone and both the aldehyde group getting reduced to their corresponding alcohol. But if we do the same reaction in the low temperature, so what happened that only selectively aldehyde group reduced to corresponding alcohol and ketone group getting intact. This is because that aldehyde group is more reactive over ketone group. So usually when we actually reduce the temperature, we are actually increase the selectivity of the particular reaction, and this happen when in the case of -10 degree temperature, only the aldehyde part getting reduced, but in 0 degree temperature or in the higher temperature, the room temperature, both the group has been reduced. And in low temperature, more reactive aldehyde group selectively reduced. Now there are some exceptional NABH4 reduction we'll discuss, that like if it is present in the diazo type of thing, like N2 is there, in presence of NaBH4 it directly form a benzene. So this is the exceptional NaBH4 based reaction. And also you have to know about the regioselectivity of NaBH4, like in the case of alpha beta unsaturated carbonyl compound. In presence of alpha beta unsaturated carbonyl compound, since NaBH4 has generated the hydride, and the hydride is actually a hard nucleophile, so it will obviously attack in the hard center. And in the case of alpha beta unsaturated carbonyl compound, the hard center is this particular carbonyl carbon center, and the soft center is this particular center, the beta carbon center. So in case of NaBH4, it's usually attack in the heart center, that is the carbonyl carbon. So 1,2 addition takes place. But the interesting thing is that in presence of these three, only these three compound, if this is your starting material, then NaBH4 shows 1,4 hydride addition. Only these three compounds. This is a very interesting exception. So you have to remember this. Like in the case of this compound, the 1,4 addition takes place. Like here is the hydride come. This particular hydride come from the boron center, and this will come from the solvent. And similarly, like if you have this type of compound, there's also NaBH4, and the hydride attacks here, and we get this particular compound. Similarly, if we have if this type of compound, alpha beta unsaturated compound on the 5-member ring, then it is also shows 1,4 product. But if it is have a 6-member ring, then it will form only 1,2 product. Like this particular bond is getting intact in case of 6-member ring, but in the case of 5-member ring, this particular 1,4 addition takes place. Now let us talk about the NaBH4 and tosyl hydrazone reaction. So if a tosyl hydrazone is there, so tosyl hydrazone in presence of NaBH4 generated this type of cyclohexane moiety. So let us understand the mechanism of the particular reaction. So what happened that this particular hydride actually attack in this particular center to generate this intermediate, and now this intermediate getting rearranged to remove this TS or tosyl part, because tosyl part a good leaving group to generate this type of part. And now this particular hydride will return back to actually eliminate the N2 from this particular mixture to generate this particular intermediate, and this intermediate in presence of a solvent quenching, it will generate this type of compound. So this is a very interesting reaction, and this particular mechanism actually confirmed by isotope labeling experiment. So isotope labeling experiment is something that we are actually using instead of using NaBH4, the people have using NaBD4, that is the isotope of hydrogen. So what happened that we get this particular product, similar product that observed here, and this product is only achievable when the particular reaction is followed by this particular mechanism. So the mechanism is confirmed by isotope leveling experiment. So with this, we have to understand that why the Luce reagent is important. So for this, basically, let us look on our previous problem that we had discussed in our previous lecture. So if you have a starting material which contains both the aldehyde and ketone group, and in presence of NaBH4, like if you go in the room temperature uh, or 0 degree temperature, then both of the group, that is the aldehyde group as well as the ketone group, both are actually reduced to their corresponding alcohol. But and in the lower temperature, in minus 10 degrees centigrade, you can do selectively aldehyde group reduce and without harming the ketone group and ketone group present there. So what if that we want this ketone group selectively reduced in presence of aldehyde group by using NaBH4 reagent? So for that reason, basically we add simply steric chloride in the reaction mixture, and this is actually the birth of the Luce reagent. So if we want to do selectively reduce the ketone group in presence of aldehyde group in the same molecule and by using NaBH4, then we can use the Luce reagent. And the Luce reagent is nothing but the NaBH4 and steric chloride and water combination of this. And the importance of the Luce reagent is it is selectively reduce the ketone group in presence of an aldehyde group in a same molecule. Just here you can see that the same molecule contains a ketone group and the aldehyde group. Now if you want to selectively reduce the ketone group, then we can use the Luce reagent to see the ketone group getting reduced to their corresponding alcohol, but the aldehyde group doesn't participate in the reaction, and this is the 1,2 hydride addition. And this is because of the fact that the steric is here, the C is actually chelating with this particular ketone part, makes this particular carbonyl carbon become much electronegative, much electrophilic in nature. And since this particular center become more electrophilic in nature, that means this particular center now attract more nucleophilic attack. Like here in NaBH4, we know that the hydride is nothing but a nucleophile, and this will more attract to this particular center because now this particular carbonyl carbon center become more electrophilic, and that's why this particular felicitate. Now you may be asked that why this type of selectivity is observed, because here also steric will do chelation, but selectively here only chelation favors. So we'll discuss in our subsequent slides this particular part. Okay. So here it is written that Ce3 plus chelates with the ketone oxygen. This is very important. Why we'll discuss in our next next slide or subsequent slides. But remember that in Luce reagent, the Ce is actually chelate with the ketone oxygen more rather than the aldehyde oxygen, and hence it is increased the more electrophilicity in ketone carbon, and hence the particular transformation is observed. So first let us understand the mechanism of this particular thing. So there is a two different mechanism is there. The one mechanism is first that steric chloride is actually mixed with the NaBH4 to form this type of compound. Now this HCeCl2 have both the properties, like it is a Lewis acid due to the presence of this Ce group, and also it have the hydride donor. The hydride donor is nothing but this hydrogen. This will act as a hydride donor now. Now what happened that in this step 2 mechanism, you can find that it is a concerted mechanism where this particular Lewis acid, that is the Ce acidic, is actually chelate with the oxygen of the carbonyl compound or the ketone part. And what happened that it due to this chelation, the electrophilicity of this particular carbon center increases manifold, and so this particular hydride now attack here in a concerted fashion to make this type of compound, and after that the solvent workup there or solvent quenching takes place to break the chelate bond to get this particular our compound. And due to this particular thing, only 1,2 attacks favor in the case of Luce reagent, irrespective of all the alpha beta unsaturation is there or not. all the cases 1,2 attacks favor due to this mechanism. Okay, so there is another mechanism is also there where actually solvent plays an important role to make the nucleophile or hydride donor strong. So what happened that here this is the boron BH4 minus. So it is a soft nucleophile. Okay, now in presence of uh, alcohol solvent, in presence of acidic chloride, so it will generate this type of RO minus, which actually attach with this particular boron. And now since this particular have due to the donating electron donating ability of this particular OR, so what happened, the negative charge has been much more build up. Like here you can see that all the H has been replaced by OR, and since it is a electron donating group, so what happened that it will donate the electron density. So the electron density in the boron center become much higher, and that's why it has become a hard nucleophile because of the large charge separation. And that's why actually what happened that when it will combine with this particular alpha beta unsaturated carbonyl component combined with the acidic chloride. After chelating, this particular center become hard, and now this particular hydride it also become an hard. So what happened that hard interaction is much more facile in nature. So that's why this particular uh, attack favors, and that's why actually we can say that this is purely a 1,2 addition product, not 1,4 addition product, because since the nucleophile become is now much more hard, as well as the due to this chelation the electrophilicity of this particular carbon become much increase or increase manifold, and that's why the center become much harder center. So hard interaction become much more favorable, and that's why in all circumstances only 1,2 addition takes place. Now depend upon the stereochemistry. Now since it is a chelation takes place, so in presence of another chelating group adjacent to the carbonyl compound actually influence or alter the stereochemistry, and the stereochemistries determine the cram-chelate model. So if you want to learn about the cram-chelate model, then you can visit the asymmetric synthesis lectures. uh, if it is uploaded, then you can find in lecture 1 or 2 there is a different stereochemical models we have discussed, and there you can find this particular cram-chelate model. Okay, so as I already discussed that the Luce reagent is purely a 1,2 addition reaction. So here you can find that this particular 5-member alpha beta unsaturated carbonyl compound in the case of NaBH4 where the 1,4 addition takes place, but in the case of Luce reagent the 1,2 addition takes place, and this is the major product. Okay, so this also proves that the Luce reagent based reduction is purely 1,2 addition product. Now let us talk about the chemoselectivity that I already discussed in our second slide itself, that why there is a affinity of Ce3 plus to chelate with the ketone itself rather than aldehyde. And due to this affinity actually makes the reaction chemoselective in nature. So basically what happened that the reaction is chemoselective because in the reaction condition, that is our in presence of alcohol solvent, the hydrate formation happens in aldehyde group, and aldehyde group marks due to this. So let us understand this with this particular diagram. So what happened in the case of aldehyde, you can find here that there is only one alkane group is there, alkane or alkyne group is there. So which actually pushes the electron density to somewhat stabilize this particular electron deficiency in this particular center. So but on the other hand, it is an hydrogen, so it is not pushing any inductive effect, shown any inductive effect. So what happened that this particular center becomes a reactive. So what happened with this particular presence in present of this particular alcohol solvent, what happened that this type of hydrate formation takes place because this particular CO is highly polar bond in nature. So what happened, the electrophilicity is much higher here, and this the higher electrophilicity often lead to formation of this type of hydrate. And since it is a formation of hydrate, now there is a no chance of chelating. But in the case of ketone, if you find here, then the both side the alkane group is there, So this both alkane will have their own inductive effect, which actually stabilize or reduce the electrophilicity of this particular center. And to reduce this particular electrophilicity of the center, this particular ketone are actually preserved throughout the reaction, ketone structure, and this type of hydrate formation is less favorable here. So you can see the arrow like between this particular these two structure. Okay, so in aqueous solution, these two structure, this getting much more favored in the reaction medium, and this carbonyl structure is allow the CeCl3 to chelate, and that's why in presence of both the group aldehyde and ketone, the ketone group has the highest possibility of chelating, and that's why the chemoselectivity is observed. Class we are mainly focused on the uh, other NaBH4 derivatives such as sodium cyanoborohydride and sodium NaBH4 NaBH3OAC or NaBHOAC whole thrice. So before starting our initial discussion, let us talk about a little bit of stereochemistry of NaBH4 reduction. So since NaBH4 is a small reagent, so it will attack from the both side, like from the upward direction and the downward direction. However, the majority will decide on the steric factors. Like here you can see that this is the cyclobutane type of structure. Okay, so in presence of NaBH4, since this particular methyl in the above direction, so as you know that this particular cyclobutane are present in this type of Packard formation. So I have discussed everything about the dynamic stereochemistry of conformers in our conformational playlist. So if you don't know about this, then I will highly suggest you to visit that particular lectures also, where I will show this type of geometry or type of conformational stability in the 3D space. So you have to go there. So here you can see that there is a two possible pathway of any hydrate to attack. Like one pathway is here and one pathway is here. Now in the hydrate can attack from the both pathway. If hydrate attack from this particular pathway, then the OH become in the dash bond and the hydrate become the wedge bond. And if the hydrate attack from the lower region, then hydrate become in the dashed bond and the OH become in the wedge bond. Now this both the structure is observed, but this type of this structure is a major, because here if the reagent approach from this particular center, you can find that there is a diaxial interaction observe, or the particular hydrate will face the diaxial interaction, and that's why the other product become minor product, whereas the hydrate attack from the lower side will generate the major product of the particular reaction. Similarly, in the case of cyclopentanone type of structure, like as you already know, I hope that the cyclopentanone will stay in the open envelope form. So here you can find here that here if the hydrate goes from this particular site, then what happened that it will face interaction or the steric hindrance due to this particular methyl group, and that's why this particular hydrate will prefer to attack from the upper side to keep this particular OH in the lower region. So what happened that this particular hydrate is present in the wedge bond, where the OH present in the dashed bond. So that's how we will determine the geometry of the particular product while reduction NaBH4. Now let us talk about the NaBHOAC whole thrice. So how to prepare this particular reagent? Like simply you will add NaBH4 and the acetic acid will react to generate this type of reagent. Now if we look about this particular reagent, it is bulky because of this particular addition of this particular SCO part. The reagent become bulky, and since it is a bulky reagent, now the stereo selectivity getting increased. Like in the case of previous part, as we already discussed, that NaBH4 is small reagent, so it will attack in the both of the cases. So maybe it happened that this particular product as well as their minor product will have 60-40 ratio. But if we want to increase the yield of this particular this particular product more, then we can increase the bulkiness of this particular reagent, and thus actually done by the NABH OSA whole thrice. It actually increase the bulkiness, and with this, when this particular attack here, so it will more and more attack from the lower hand side to eliminate the steric hindrance. So gradually the yield of this particular is increasing. So and thus the selectivity getting increased. And but since it is a selectivity is increased, but it is a less reactive reagent, so the chemoselectivity is also changed here. So this particular reagent is only limited to imines and iminium ion and aldehyde group reduction. Ketone are not reduction in normal condition by using this NABH OSA whole thrice. Okay, and it's a mild reaction condition, room temperature the reaction happen, and offer high selectivity for reductive amination. Okay, and reductive amination is nothing but this. So basically what happened that this is our iminium ion. So it is a formation, how to form the iminium ion, you can see here. And after formation of iminium ion, then NaHbOSA whole thrice will attack here, the hydride will attack here to form this type of compound, and this is the compound of reductive amination. Okay, now let us talk about the another NaBH4 derivatives. It is sodium cyanoborohydride. It is a very important reagent because this reagent is a pH dependent reagent, NaBH4. It is also milder than NaBH4 at pH 7, and it is a highly pH dependent reagent. That is the very selling point of this particular reagent. Like this particular reagent is the pH dependent, and it actually tolerates the acidic condition, where actually in NaBH4 the acidic condition is not tolerable sometimes, because there is some kind of starting material is there which actually contains an acid tolerative functional group, and to that tolerate the acid tolerance functional group is there, then NaBH cyanoborohydride is used for that particular reactions. And it also shows the chemoselectivity in different pH condition, like at pH 4, less than 4, in the highly acidic condition it readily reduces aldehyde and ketone, but in the basic condition, when the pH is greater than 7, then it is reduced iminium ions only, but the carbonyl groups is not getting reduced at higher pH condition, or we can say that in the basic condition. And this is the most selling point of this sodium cyanoborohydride mediated reaction. So here you can see here that in aldehyde or ketone, in presence of sodium borohydride at acidic condition, it generate the corresponding alcohol, but in the higher pH condition no reaction has been observed. It is very important. And herein also you can find that this react with NH3 to generate the iminium ion, and after that the sodium cyanoborohydride will donate the hydride here to form this type of amine group, and this is actually happening in the higher pH condition. But in the higher pH condition, this particular aldehyde or ketone or the carbonyl groups not getting reduced by using sodium cyanoborohydride. And also sodium cyanoborohydride shows some different reactions. Like first we can say the reductive amination. Here is also, it is a nothing but a reductive amination reaction. This particular, where the iminium ion is initially generated, and after that by treating with sodium cyanoborohydride we got this particular amine group. So the reductive amination takes place by using this type of sodium cyanoborohydride. Also sodium cyanoborohydride is used SN2 reaction. Like here you can say there is a carbonyl group is there, and also there is a leaving group is there. Since we know that in neutral condition or the basic condition, sodium cyanoborohydride doesn't react with the carbonyl compound, so this particular hydride will actually perform a SN2 reaction here, and this particular OTS, that is a good leaving group, is actually leaving from the particular reaction starting material, and we got this type of product with keeping our carbonyl group intact. Okay, and also it will show the carbonyl group reduction in the lower pH condition or acidic condition. It will reduce the carbonyl group to their corresponding alcohols. So this type of reduction has been shown by sodium cyanoborohydrate, and it is a highly pH sensitive reagent. This particular class onwards, we are starting with some lithium based reducing reagents such as lithium borohydrate and selectrides. Okay, so first talking about the lithium borohydrate, that it is much more reactive version than NaBH4, and it is a commercially available solid form, and it is also moisture sensitive just like the NaBH4, and it is commonly used for the selective reduction of esters and lactones. Like LiBH4 can do reduction of carbonyl compound, as well as it is commonly used to selectively reduction of esters and lactones, whether the NaBH4 is restricted towards the ketone compound only. Okay, and also the LiBH4 is a very solvent dependent reducing agent, and it is works good with ether, THF, and 2-propanols. And here 2 hydride used in this particular mechanism, and it is less hindered site preferred attack hydride attack takes place. So here you can check the example, like here in this particular starting material there is a two functional group. One is the ester functional group, one is a CN a functional group. So LiBH4 selectively reduce ester to its corresponding alcohol, but the CN group are not affected by during this reaction. So functional group tolerance, that LiBH4 doesn't reduce CN, cyano, NO2, amide, carboxylic acid, and alpha beta unsaturation compound. Okay, so here you can see this is the big example where it is our starting material. That starting material contain different type of groups. Here you can see the amide group is there, also NO2 is there, halogen is there, ester is also there. So while treating with LiBH4 and THF, you find that only selectively the ester group is actually reduced to their corresponding alcohol, whereas the other functional group getting intact. So it is a very chemoselective reaction. So what should be the mechanism of this particular reducing mechanism? So here you can find that LiBH4, it is actually first the lithium, it goes chelate with the particular ester group, and due to this chelation actually the electrophilicity of this particular carbon is increased, and that's why this hydrate attack got felicitated. Now, this hydric attack got felicitated, and this particular negative goes back to cleave this particular CO bond here to generate this type of compound. Now this particular O minus actually quenched by taking the proton from the solvent itself, so it will generate an aldehyde, and here you can see that OH is there. So but as we know that LiBH4 is actually reduce ester to directly alcohol, so that means that the medium contains the LiBH4 will again transfer hydride here. First it will coordinate with this particular mm, aldehyde oxygen to increase the electrophilicity here, and then this particular hydride attacks to generate this type of intermediate. Now this particular intermediate will take proton from the solvent itself to generate our this type of dihydroxy compound. Okay, two OH is there, one is the primary alcohol, both are the primary alcohol here, and you can find here that two hydrides are actually attached, so that means there is a two hydride actually donated during the reaction. Now let us talking about the superhydride and K and L selectride. Like this is the similar kind of lithium borohydride, but where this particular H has been replaced by the different R, and depending upon the R group, it actually have different names. Like where the metal, when metal is the lithium plus and the R's are nothing but the ethyl, then it is called a superhydride. But when the R group is sec butyl, when the metal is lithium itself, then it is called the L selectride. And if the metal has been changed to lithium to potassium and the sec butyl is the R, then it is called as a K selectride. Now these three reagents have their unique reactivity, so we'll discuss in the next slide. So first we are talking about the superhydrides. Superhydrides are highly reactive reducing agent. Basically it is done SN2 type of mechanism. It follows the SN2 type of mechanism where this particular RX bond there, when we treat it with superhydride, then what happened, that X group is replaced by this particular hydride here, and to form the RH bond. And what should be the X group there? X group should be OH, NH2, OTS, OTF, OBN, and halogens. Okay, so here is a simple example. Here you can find that this particular KH type of molecule is there, which contains CH2 and OTS bond. So what happened, that superhydride, the hydride is actually attack here, and via SN2 mechanism it will generate this particular compound. Okay, and the structure is something like this. Now let us talk about the K and L selectride. It is K and L selectride is nothing but a lithium and potassium trisec butyl borohydrides. And as we know from the structure itself, since it is the R group is the sec butyl, so that means it is a bulky reagent, and it is reduced aldehyde and ketone even minus 78 degrees centigrade. So it is a low temperature. If we go via low temperature based reaction, then also K and L selectride is able to reduce aldehyde and ketone. And it is a stereoselective reagent, and hydride attacks, this particular hydride attacks are from the less hindered sites because of the steric issues. Like already as we know that this particular L selectride and K selectrides are actually bulky in nature, so obviously to eliminate the steric repulsion, they will attack or they will transfer the hydride from the less hindered side of the product or the reactant. Now here you can see the particular example, like this is our starting material, that is alpha beta unsaturated carbonyl compound, and when treated with K or L selectride, we got two different products. One is the 1,2 attack, like here the hydride goes transferred, and in the second case the 1,4 attack, that means here is hydrogenous transfer. As we already discussed that K and L selectride are bulky in nature, that's why the bulkiness or the steric factors actually determine that the hydride attacks, where will the hydride attacks goes. Now the 1,2 attack is felicitated when R1 and R2 both are alkyl or aryl. Like if these two particular group bulky enough, then hydride can't transfer from here. That means in that particular scenario, when the R1 and R2 are bulky enough, then only 1,2 addition takes place. Similarly, if the R1 and R2 are hydrogen or kind of small group which contains the less steric bulk, then this particular hydride transfer from the 1,4 position. Okay, so we are actually see this particular trend in this particular following example. Here you can find there is a two different center is there. This is also 1,4 additional place, and this is also 1,4 additional place. Now here you can find these two particular are bulky group. That means hydride transfer become much more sterically hindered in this particular center. So here it will not actually uh, uh, not attack from this particular center, but whereas that here you can see this is also alpha beta unsaturation position, and this particular 1,4 position you can find that two hydrogen is there, that means the less steric bulk is there, so it will initially attack from here, this particular bond goes there, and this got a negative charge. Now in the second case you can say the ethyl iodide is there, so that means what happened, that I am just changed the ink color. So this particular negative charge go back, and here the partially the double bond has been formed here. This particular double bond that actually attack here to eliminate the iodine, and finally we got this particular product exclusively. So that means we can say that it is a regioselective regioselective pathway has been followed here. So it is written here that is the less hindered side is a more sterically hindered center, and that's why this type of reaction actually felicitated. Here today we will discuss about some more nucleophilic reagent which is much more stronger than those reagent, that is the zinc borohydride and lithium aluminum hydride. So first let's talk about the zinc borohydride. that zinc borohydrate is a stronger reducing agent than NaBH4, lithium borohydrate, and selectrides. Okay, and it is also a moisture sensitive reducing agent and stereoselective. Also, it will reduce the carbonyl ester and acid group. And also the important feature of this particular zinc borohydrate, it selectively reduces aldehyde in presence of a ketone. And it is also conjugated aldehyde is reduced, and the reaction mixture that aprotic solvent has been used, that DCM, DMF, THF, this type of aprotic solvent has been used, and acyclic uh, acyclic conformer is more reduced than cyclic system. And when if it is an isolated double bond presence such as this type of thing, then hydroboration observed. Okay, so what should be the reaction? Reaction is if it is an acid moiety, that is benzoic acid, and benzoic acid react with the zinc borohydrate in presence of aprotic solvent THF to getting their corresponding alcohol. And the structure of this particular zinc borohydrate is this. Now let us talk about the chemoselectivity. Like as I already discussed, that if the particular starting material contain both the aldehyde and ketone group, then zinc borohydrate is actually selectively reduce the aldehyde group and leaving the ketone group intact. Okay, so also here you can see that this is our acid moiety and this is our isolated double bond. So in presence of zinc borohydrate, it can reduce both. Like here, it will go via hydrate transfer reagent and to form this type of primary alcohol. Whereas this particular isolated double bond, it is the hydroboration takes place where the anti-Markovnikov addition takes place to get this type of compound. Now let's talk about the regioselectivity. As I already discussed in the previous slide, that acyclic is more reduced than cyclic system. So here you can find that is a both the carbonyl compound, where this particular is the acyclic ketone and this is a cyclic ketone. Now zinc borohydrate is actually reduce this acyclic ketone more or selectively over the cyclic ketone. So this is the overall summary of the zinc borohydrate. Now let us talking about the very interesting reducing agent. This is the lithium aluminum hydride or LAH. In physical property, it is grayish in color and it is completely non-selective reagent for hydride transfer reduction. Like all the group, carbonyl, esters, then carboxylic acid, amide, all the groups are actually reduced by using lithium aluminum hydride, and also many other functional group has reduced to or eliminate. And reaction with acidic proton generate hydrogen, and reaction condition is very harsh, minus 78 degree temperature, and ether solvent is required for this particular reaction because lithium aluminum hydride is pyrophoric in nature, so it tends to catch fire in presence of air and moisture. That's why the reaction condition is very harsh, and it will reduce everything except double bonds. Okay, so let us talk about the mechanism. Mechanism is as similar as the sodium borohydride. Like here, that first the lithium got coordinate with this particular carbonyl oxygen. So the arrow will be in opposite direction. So the lithium get coordinate with this particular oxygen to increase the electrophilicity of this particular carbonyl's carbon center, and then this particular hydrides is actually attacks to generate this type of intermediate, and then on also you can find that three different hydrogen is there to generate the corresponding hydride. So after doing workup, so 1 mole of lithium aluminum hydride generate 4 mole of hydride. So that means 1 mole of lithium aluminum hydride will able to reduce 4 mole of carbonyl compound or something this, and this is the byproduct. And it is the mechanism is purely similar to the NaBH4 based reduction. So whereas the one of the hydride is come from the reagent and of the hydride is come from the solvent itself. Now you can find that very interesting trend from the class where we are starting the reducing agent, nucleophilic reducing agent. So as we go down from sodium borohydride to lithium borohydride, then you can say the reactivity is increases by many fold. and also the selectivity is also decreasing. Like in NaBH4, it is specialized to reduce the carbonyl compounds, but in the case of lithium aluminum hydride, it can reduce everything. So why did it so? So there is a basically two reason is there with this particular problem. So the reason behind this trend is, one is the bond polarity and the second one is the charge density of the counter ion. So first you can see that between the BH and aluminium H. So what happened that this particular bond is more polar in nature over the BH bond, and since this particular bond is more polar, that means the hydride generated from this particular bond is actually much more stronger or much more nucleophilic in nature than this particular BH generated hydride, BH bond generated hydride, and that's why actually the groups contains the aluminum hydrides are more reactive. Just here is a lithium borohydride and lithium aluminum hydride. Both are same counter ion, that is a lithium. But since it is the BH is there and is the ALH is there, that's why lithium aluminum hydride is more reactive than lithium borohydride. And the second thing is the charge density of the counter ion. The charge density of the counter ion says that the more charge in the particular ion, that means the more charge density, obviously. Okay, so that's why the zinc having a +2, that means it has the higher charge density. Now between sodium and lithium, both are having +1 charge, and you can know that between lithium and sodium, lithium have a smaller radius, and due to the smaller radius, the charge density of the lithium is much higher over sodium, and that's why actually the trend continues that the sodium borohydride getting the lesser reactive, and the lithium borohydride is the more reactive than sodium borohydride, and zinc borohydride is much more reactive over these two because of the charge density. And the lithium aluminum hydride is more ultimate stronger reducing agent because it has the ALH bond, the bond polarity, it will be highest bond polarity over these three, as well as there is a good amount of charge density, and that's why this two factor actually helps lithium aluminum hydride to be the best or the strongest nucleophilic reducing agent. Okay, so now let us talk about the lithium aluminum hydride based reactions. But before that, we're talking about a little bit of selectivity. Like if you have this type of compound where it has several functional groups. Now, if we want to target any kind of one specific group, like if you want to reduce only the carbonyl part of this particular group and keep this two particular other functional group is untouched, then you can use sodium borohydride. Sodium borohydride is selectively reduce the carbonyl part only. Now, if you want to reduce the ester part only, then you can use the lithium borohydride. The lithium borohydride is reduced preferably esters, and these two getting untouched. However, that some time that this particular carbonyl group is also reduced, but in major amount of you can get this type of compound. And if you don't want any kind of selectivity in your reaction, like if you want that every group present in this particular starting material got reduced, then simply use lithium aluminum hydride, and you will get this type of compound, like all of the functional group has been reduced. Now let us talk about the lithium aluminum hydride based reactions. So here it is a lithium aluminum hydride. Now lithium aluminum hydride react with the azides, that is the Rn3, to getting the amine. Similarly, it will react with the acid chloride to generate the corresponding alcohol. It will react with the ketone to getting corresponding secondary alcohol. It attacks or it reacts with the aldehyde to generate the primary alcohol. Similarly, it reduces ester to their corresponding alcohols. Carboxylic acid is also getting reduced by the lithium aluminum hydride to generate this particular alcohol. Also, the amide and cyano also reduce to their corresponding amines. And if it is an epoxide, then it will attack from the less hindered side. The hydride attacks comes from the less hindered side, and it will generate secondary alcohol. So you can find here that lithium aluminum hydride is basically reducing everything except double bonds. Now let us talking about similar kind of reducing agent, that is a red aluminium. Red aluminium, the full form is the sodium bis 2 methoxy ethoxy aluminium hydride, or it can be termed as SMEH or red aluminium. And the structure of this particular compound is this. This shows the similar reactivity of lithium aluminum hydride. However, it will show some different reactivity also that I will discuss in the next slide. So first, let us talking about some information regarding the red aluminium. So first, it is a moisture sensitive reagent, and the second is that it is shown the similar reactivity like lithium aluminum hydride, and it has longer shelf life, and it is thermally stable up to 200 degrees centigrade. And since it is a replace the lithium to sodium, and that's actually makes the shelf life of this particular reagent is much higher, and also not harsh condition is required while using red aluminum hydride. And this is the much more advantage of using red aluminum instead of using lithium aluminum hydride. So let us understand that what kind of unique reactivity shown this particular red aluminium. So red aluminium show similar reactivity like lithium aluminum hydride. However, it shows some more unique reactivity than lithium aluminum hydride, such as that reductive cleavage of ether. Like here you can cite that OBN, like if you attend the protection deprotection class, then you can find that OBN is something this. Now this is nothing but ether. Like in presence of red aluminium in xylene, in reflux condition, this particular bond actually cleaves, and it will reductive cleavage of ether has been takes place to generate this type of alcohol. Also, red aluminum is useful reagent to debenzylation and dearylation of aryl benzene and aryl ethers that are already discussed here. Also, it can do selectively reduction. Here you can find that alpha beta unsaturation is there. Okay, in presence of this red aluminium in reflux condition, you can selectively reduce this particular double bond. Okay, so this is the unique reactivity that a lithium aluminum hydride can't do. And also it will do a stereo selective epoxide opening, like when unsymmetrical epoxide are there, then the hydride attacks are preferably in the less substituted site to give the highly substituted alcohol as the major product. Like here you can find that between this particular center, depending upon the R group, this is the less hindered. So the hydride attacks from here, and this particular bond goes up and to generate this as a product, and the stereochemistry will based on the reactivity. Similarly here also, this is the less hindered side, so it will transfer the hydride from here and not here, and it goes down to get our this type of compounds. Also, in lithium aluminum hydride, it can't react with the double bond and triple bonds, but in the case of red aluminium, it will react with the triple bonds also, and also stereo selective part. Like if you have this type of system, this type of triple bond system, then if you add 4 equivalent of red aluminum hydride or 4 equivalent of SMEAH, then you can find that a trans product is the major one. But if you increase the amount of SMEAH, that is the 8 equivalent or the higher equivalent, then cis product is observed. And this is the stereo selective reaction. And this is because of the particular reason that this particular oxygen actually chelate with the Al present there, and it actually facilitated the reaction condition. Example, here you can find this particular reaction. Okay, so what happened that here you can see that 1.2 equivalent of SMEH has been used. That means the lower amount, and that since it is a lower amount of SMEH used, that means the trans product has been formed. So the mechanistic pathway is that particular Al is actually chelate with this particular oxygen to direct the hydrate transfer pathway, and due to the direction of hydrate transfer pathway, this hydrate transfer from here and this particular bond goes up to getting our trans product over cis. So let us talk about the summary of our all nucleophilic reduction agent, and this is the master slide of our whole lectures from lecture uh, 3 to lecture 8. Okay, So first let us talking about the reducing agent. NaBH4, imine reduction has been possible. Acid chloride has been reduction possible. Aldehyde reduction possible. Ketone is also possible in room temperature or higher temperature, but in lower temperature ketone is not possible. Ester is usually not reduced by the NaBH4 in standard condition, but if you increase the amount of NaBH4, this is 5 equivalent or 6 equivalent, then it can reduce the ester also, but it is a very harsh condition is required, so we are not dealing with the ester reduction by using NaBH4. And acid and amide are not reduced by NaBH4. Now, if we call about Luce reagent is actually reduce still ketone, but it will not reduce ester, acid, and amides. Now, NaBH3CS, the cyanoborhydrate is purely pH dependent. In lower pH condition, it actually reduces aldehyde, but ketone is not reduced by this. And in higher pH condition, it will nothing. The aldehyde is also not reduced, but imine and acid chloride has been reduced by the sodium cyanoborohydrate. Now let us talk about the lithium borohydrate. Lithium borohydrate has able or capable to reduce still ester, but it will not capable to reduce acid group and amide group. Zinc borohydrate like zinc BH42. So this particular reducing reagent has capable to reduce still acid, but it will not able to reduce amide. And lithium aluminum hydride and red aluminium, it will reduce all the functional group present here. So this is a summary of our nucleophilic reducing agent. So reducing agents in brief. So now today onwards we are starting about the electrophilic reducing reagent. And in case of electrophilic reducing agent, two reagents are very important in terms of exam point of view. That is a dival H and the BH3. So we will learn these two reagents today. Okay. So let us start with our discussion with dival H. So first of all, what is the full form of dival H? The full form of dival H is diisobutyl aluminum hydride, and the prefix has taken to form this particular dival H. And it is a structure something like this. So there is the aluminum is there, and there is the one hydride, and two diisobutyl is attached here. And now, since it is an electrophilic in nature, that's why this particular reagent present in the dimeric form. So the electrophilicity of aluminum getting reduced. So let us understand some information regarding the dival H. So first, it is an organoaluminium hydride donor. It is an electrophilic in nature, that's already discussed. And the interesting thing is this particular dival H is air and moisture sensitive, and it is a pyrophoric in nature. That means it catches fire in presence of air. So actually, this is the reagent that actually used in a low temperature. The reaction carried out in a low temperature because of this particular pyrophoric nature. Okay, and it is a temperature dependent reagent. Like low temperature, it will show another selectivity, and a higher temperature, it will show another selectivity. And the associated solvent with this particular reaction is ether, THF, DCM, and toluene. And the workup can be done by using methanol and water. So what is the role of dival H in this particular reaction? So dival H basically generate aldehyde. Okay, so if you want to generate ester to aldehyde, or you can stop the reaction in aldehyde position, not in the alcohol position, then you can use dival H. So in low temperature, it will reduce ester to its corresponding aldehyde, not alcohol. So it is a aldehyde generator, you can see. Okay, but in the case of higher temperature, this ester is reduced to the alcohol. Now it is not stopping in the aldehyde part. And not only ester, actually it will reduce cyanide group to their corresponding aldehyde. Okay. So let us understand the mechanism of this particular reaction. First, we know that Al is the electrophilic in nature. That means this particular lone pair of this oxygen will donate to Al to generate this type of bond. And here you can find that it will now this hydride come in the closer proximity of this particular carbonyl carbon. And now since this particular OAl bond takes place, so that's why this particular center, there is a carbonyl carbon center, become much more electrophilic, which facilitated the hydride attack here. Okay, and it is a four-member transition state has been formed. If you check here, like 1, 2, 3, and 4. So there is a 4-member transition state has been formed, and this is the intermediate that is generated. Now, interestingly, since we are actually doing this particular reaction in the low temperature, it is a minus 78 degrees centigrade. So what happened that this particular intermediate that actually formed is very much stable in 70 degree, and that's why the product has been stopped in the aldehyde part, and the further reduction is not observed since this product this is much more stable in nature. But in the higher temperature, what happened that this intermediate is not that much stable. That's why after generating the aldehyde, then it will further reduction takes place to generate its corresponding alcohol. Okay, in high temperature it will generate the corresponding alcohol. But since we are doing this particular reaction in the low temperature, so this particular intermediate, due to this intermediate stable, that's why it will stop in the aldehyde part. So we can say that dival H is a contractor of aldehyde. Like uh, in ester or cyanide group is there, it will directly reduce to aldehyde. Okay. So that's why in low temperature upon hydrolysis, that is we discussed that methanol water hydrolysis, that aldehyde becomes the major product. Now let us talk about some kind of reaction. Like here you can see that cyanide group is there and dival H is used in the minus 78 degrees centigrade. That cyanide is directly converted to their corresponding aldehyde. Similarly, if you see here, this particular group contains an ester as well as an alpha beta unsaturation. So dival H is actually as much selective that it will only reduce that ester but keeping the double bond intact. Okay, and here you can see the reaction condition, that is a room temperature reaction condition. That means it will not stop in the aldehyde, it will further reduction takes place to form the corresponding alcohol and the double bond getting intact. Similarly, dival H is used to reduce the lactone also, like it is a lactone, and the it will be also reduced to their corresponding aldehydes. And in room temperature of 0 degree centigrade, the both of the center getting reduced to alcohol. Okay. Now, dival H can actually react with the triple bond also. So dival H react with alkyne to generate cis alkene, and this is the very important reaction. Like sometime it will ask in the examination also. Like if you want to make a triple bond to cis alkyne, cis alkane, so how we will do it? So we can simply say that give the dival H, and the reason behind is this 4-member transition state, and due to this 4-member transition state, actually the cis form is predominant. Now let us talk about the BH3 or B2H6. It is also an electrophilic reducing agent, and it is selectively reduce acid group in presence of other functional group. So BH3 not only reduce the acid, it will also reduce amides also, cyanide also. So here you can see that this is the acid group in presence of BH3. It will reduce to their corresponding alcohol. Similarly, if you have aldehyde and ketone, then also BH3 getting is done the reduction to generate their corresponding alcohol. And interesting thing is amide also getting reduced in presence of BH3 to form this type of primary amine. Cyanide also reduced, or you can say that here the reductive amination takes place to form this type of thing. But in the case of double present in the double bond, then BH3 will show hydroboration, that is the anti-Markovnikov addition to generate this type of compound. So this is some kind of exception you can say. But in the case of other functional group, it will generate their corresponding alcohol or show reductive amination. Now, let us talk about the mechanism. The mechanism is simple, like dival H. So, since the BH3 is electrophilic in nature, that means this lone pair of oxygen actually coordinate with this particular BH3, so that this particular and this in the presence of amide, actually this was much more felicitated to donate the lone pair, because that amide also donate its lone pair here to get their partially double bond type of thing here, and this particular bond become much more donatable since the negative charge is actually comes here. So it will donate to BHC to make the chelate. Okay, so here is the 2 is there. So now this particular hydride will actually attack here this carbonyl carbon center, and this particular double bond or goes back. Okay, and now what happened that this particular lone pair will again go here, and this particular group is removed from the mixture, removed from the compound to generate the reductive amination product. And what is the BH3 reactivity trend? BH3 reactivity trend is first, if your compound contains acid, then acid will reduce first. Then isolated with double bond is getting reduced, not reduced, actually hydroboration takes place. Then amide, and after that aldehyde, ketone, cyanide, epoxide, and ester getting reduced. So this is the priority order of BH3 reactivity trend. Okay. So let us understand with some kind of examples. Like here you can see that ester group is there and amide is there. Now we are say the priority order of BH3, that amide group is reduced more over esters. So that's why actually in this particular reaction amides are actually reduced to their corresponding amines, but ester group is actually intact. Similarly, this particular have the acid. So in presence of BH3, acid will reduce to their corresponding alcohol. Similarly, epoxide case, the loose SN1 mechanism has been observed. Similarly, with NaBH4 that I am discussed in the class 3. So the more hindered side actually getting hydrated. So this type of product has been generated. So we're starting with the solvated metal ion based reduction, and the pioneer of that particular reduction is Birch reduction. So let us understand the Birch reaction in details. So first of all, Birch reduction is an organic reduction of 1,4-cyclohexadiene in liquid ammonia with sodium, lithium, and alcohol like ethanol or tert butyrate. So basically what happened that the initial starting product is benzene. Benzene 2,1,4-cyclohexadiene is formed, that is the reduction in presence of liquid ammonia with the metal is sodium and lithium, and as a solvent like ethanol or tert butyl. And it is a regioselective reaction, and the regioselectivity is depend on the nature of substituent in the aromatic compound. Like if a aromatic compound contains a substituent which having the electron donating nature, then the double bond regioselectivity is a little bit difference. And if the substituent are the electron withdrawing in nature, then the double bond regioselectivity is changed. And it is a radical based reaction, and the reaction proceed via single electron transfer mechanism. That means the one electron has been transferred, and this particular electron have their own significance in the reaction mechanism pathway. So let us understand the what actually the reaction done. So basically this is our aromatic compound, and where the R group is a substituent, and the metal is the lithium or sodium. Mainly sodium has been used in the Birch reduction, and also the ammonia, liquid ammonia. And this particular liquid ammonia have their own role in the mechanistic pathway, and the solvent is ether. Now here you can see that two different product is observed. Like when the R is electron donating group, then the double bond position is something like this. Whereas if the R is the electron withdrawing in nature, then what happened, the double bond position is something like this. Okay, so now let us understand the mechanistic pathway of the Birch reduction. So as I already discussed that liquid ammonia have their own significance in this particular Birch reduction. So the metal actually in the presence of liquid ammonia, it liberates one electron, and it become the M positive, and now this electron will go to do the further reduction. So what happened that this particular electron will attack here in the radical pathway to undergo a set mechanism. So what happened that here you can find that particular radical is here, and now here you got a negative charge. Okay, now what happened that this particular negative charge will abstract the proton from the solvent, that is ether, and it will make this. Now after generating this particular compound, now here you can find that there is another single electron is there. So the excess electron present in the reaction mixture will now attack here to make this particular negative charge. Now this particular negative charge will take or capture another particular hydrogen from the solvent, that is ether, to generate our this particular compound, and this is the mechanism of the Birch reduction, and this particular mechanism is called single electron transfer mechanism. Now, as I already discussed the DGO selectivity, like here it is your compound, and when the in Birch reduction condition, when the R group is the electron donating group, then this type of double bond has been observed, and whereas the R is electron withdrawing group, then this orientation of double bond is observed. Now, what should be the electron donating group and what should be the electron withdrawing group? Just remember, for the exam point of view, that if this particular R is either acid or CONH2, then you can say that this particular is the major product, this particular orientation of double bond, whereas the rest, any group present in this particular substituent part, then this type of uh, orientation of double bond has been observed. So what should be the electron donating group? That OH, OR, NR2, SR, PR2, alkyl, CH2, OR, CH2, OH, CHO, C esters, all the present in the electron donating group. Whereas the electron withdrawing group contains only two. So whenever you are preparing for the examination purpose, so you can just remember these two as the electron withdrawing group. So rest all are present in the electron donating group. However, there is a one exceptional case is there that I want to discuss here. That is in the next slide, obviously, and it is a regioselective reaction that I already discussed. Okay, so now let us talking about some example, and after that I will show the exception of this particular rule. Okay, so first let us call the substituent effect. Now, if your a particular aromatic compound contains both electron donating group but in the anti position, so what happened that this type of a double bond has been observed. Now here, if this particular electron donating group not present, then it also satisfy the previous slide, as well as for this particular electron donating group also it will satisfy the bond orientation. So this is the final product. However, if one group is your electron withdrawing group and the anti-position group is electron donating group, then always remember that electron withdrawing group will get more priority in terms of regioselectivity. That means that irrespective of the electron donating group present here, the bond orientation should be like this, which is follow the electron withdrawing group. And here it is written that influence of electron withdrawing group is more than electron donating group in this particular Birch reduction. Now here, if your electron withdrawing group and electron donating group are meta to each other, then what happened that after doing electron withdrawing group configuration, or we can say regioselectivity of double bond, you can find that electron donating group also satisfy the particular structure, because both the cases the structure is same. Okay, now let us talk about the nap naphthalene type of compound. Like this is also an aromatic region. Now, if your naphthalene also, this is a nothing but a fused benzene ring, then if one of the ring is the contains the electron donating group and one of the ring contains electron withdrawing group, then always remember that by using Birch reduction, electron deficient ring always reduction takes place over electron rich ring. So electron deficient ring will always go for reduction in Birch reduction. For example, see here that this particular ring is electron rich due to the plus I effect of this particular methyl. However, this particular ring will not get this type of benefit. That means if we compare these two rings, then we can found that only this particular ring is the electron deficient, and that's why after doing Birch reduction, only this ring will get reduction takes place, and this particular group or ring remain unaffected. An important exception that I already discussed in the regioselective slide, that if your compound or the group that is contains NMe2, that is considered as an electron donating group. Okay, so what happened that usually we are observing that this type of homologous double bond has been observed, the regioselectivity is something like this. However, for this particular example only, this particular transformation or isomerization happens very quickly. That's why actually, and this is due to the because of this particular lone pair donation, and that's why actually we observe this particular structure. So I just simply clear here, and you can find, and we got this particular structure as a major, so it is a important exception over other Birch reductions. Now let us talking about the reductive alkylation of Birch reduction. So this is the extended part of the Birch reduction, where what happened that after doing Birch reduction, if we don't put solvent and if we put any kind of alkyl group or alkyl halide group, so it got a reductive alkylation. So the mechanism is simple, like initially this particular negative charge is generated, and now this particular negative charge is stable due to the presence of electron withdrawing group, and that's why actually in presence of an alkyl halide, this particular negative charge will attack to remove the halogen bond to get this type of compound, and this is called the reductive alkylation. Okay, and here you can find in this particular example, now the negative charge always stable when it get adjacent electron withdrawing group. Now this is a electron donating group, but this particular CONH2, this is the amide, this is a electron withdrawing group, and since it is a electron withdrawing group, this particular negative charge is stable here, and that means the alkylation takes place on this particular side. And here you can find the stereochemistry, because this particular is present in the lower side of the paper, or we can say that away from the observer. So what happened that this particular stereochemistry will be the above to the paper, or we can say that near to the observer. Okay, and here it is an important line is written that when negative charge are stable, then alkyl addition takes place. Now alkene reduction, this is the very important, like when we treat a alkene, there's a triple bond with Birch reduction condition, then Birch reduction always gives the trans alkene, and this is the stereoselective in nature, and this might become in the questions. Okay, and ketone reduction is also done by the similar fashion, where this particular electron will attack from the top side to make this particular ketone is the lower end to generate this particular compound. Okay, and also let us talk about the alpha beta unsaturation compounds. So in case of alpha beta unsaturation compound, Birch reduction is usually show 1,4 addition. So what happened that this particular electron that is generated from this particular Birch reduction condition, it will attack here, and this particular bond goes here and this goes here. And after that it also have the solvent, so that solvent will give this particular hydrogen. And here you can find that ETOPOCl, this particular reagent is actually used for the selective reduction of the ketone, like this actually responsible to break the CO bond here. So what happened that after doing this particular thing, this particular first initially attach with the O, and then this particular bond cleaves apart in presence of Birch reduction condition, and we got this particular final product. Now there are certain examples, like here you can see that this is the same example, that is the break CO bond, and also if we get the norboryl system, then it also shows the Birch reduction and give the endo product. The hydrogenation by using metal catalysis. Okay, so first let us understand the hydrogenation. Basically you all know about the hydrogenation. Hydrogenation is nothing but a hydrogen addition to an unsaturated compound to make this saturated. Okay, now here hydrogenation can be done by various process, but here we are actually focused on the metal catalysis pathway. Okay, so now hydrogenation we can simply classify in three different part. This is the homogeneous hydrogenation, heterogeneous hydrogenation, and asymmetric hydrogenation. Homogeneous hydrogenation suggests that the catalyst is actually catalyst and your the compound having the same phase, whereas the heterogeneous hydrogenation means that the catalysis and your reactant are in the different phase. And asymmetric hydrogenation, that means the stereoselective hydrogenation that we are actually not discussing here. Asymmetric hydrogenation we will discuss in our asymmetric synthesis part. Okay, so we are mainly focused on this particular two. This is the homogeneous hydrogenation and heterogeneous hydrogenation. So homogeneous hydrogenation is a single phase reaction, and the heavy metal based catalysis has been used, whereas in heterogeneous hydrogenation it is a two phase reaction, and basically palladium or nickel based hydrogenation takes place. And this particular reaction, that is the hydrogenation as a double bond, is thermodynamically favorable, and that's why actually this reaction is felicitated. Now let us talk about the homogeneous hydrogenation in details. But before that, we have to know that ease of reduction of functional group to a catalytic hydrogenation. Okay, like if you see this particular group, that you can find here that by using catalytic hydrogenation, that means the metal catalysis, by applying metal catalysis, benzene to cyclohexane is the hardest reduction to do, because here actually we are losing the aromaticity, so it is the hardest to do. Now as we go up to this particular arrow and the functional group comes here, this is the easiest to do hydrogenation by using catalysis, metal catalysis. Like the most easiest job to do hydrogenation by using metal catalysis is acid chloride to aldehyde, then NO2 to NH2, then here is the RC triple bond C, this is the triple bond, or you can say the alkyne to alkene transformation, then aldehyde to alcohol, then double bond to single bond, and then ketone to their corresponding alcohol. So you can find here that the most difficult task to do is benzene to cyclohexane, and the most easiest task to do by catalytic hydrogenation, that is the acid chloride to aldehyde. Okay, so now let us talk about the homogeneous hydrogenation, and here we are mainly focused on the Wilkinson catalysis. Okay, so Wilkinson catalysis is a homogeneous hydrogenation, and it is nothing but this, that rhodium triphenyl phosphine whole 3 chlorine. Okay, so this is the our catalysis, and this is the organometallic compound, and it is show the syn hydrogenation. Okay, this is the stereoselectivity, like syn hydrogenation takes place. Less substituted double bond has been reduced first. Isolated double bond reduction more than conjugated one. This thing we had actually discussed in when we are doing actually question answers. Now the most important thing is what should be the mechanism of this particular Wilkinson catalysis. So the mechanism is the traditional organometallic compound have their own cyclic mechanism, where three major steps has been observed. First one is the oxidative addition. Oxidative addition is basically nothing but that the reactant are actually add to the metal catalysis, then hydrate transfer, and then reductive elimination. Reductive elimination means the product has been removed from the catalysis. So we'll discuss in brief or in elaborate way in the mechanism. But before that, we have actually see this particular reaction. Now here you can see that here two type of double bond is there. One is the exocyclic double bond, or we can say that isolated double bond, and this is the substituted double bond. Now in presence of Wilkinson catalysis, what happened that the selectively that isolated double bond has been reduced. However, this particular double bond is not reduced. Okay, so you have to remember this small thing. Now we are talking about the mechanistic pathway. So the mechanism is the initially this is our the catalysis, rhodium triphenyl phosphine whole 3 and chlorine is there, and if you calculate the electron number, it is a 16 electron species. That means it has a vacant site. Okay, now this particular hydrogen actually attach with this particular thing via oxidative addition, because here the rhodium is +1 state. After addition of hydrogen, rhodium is now +3 state. That means the oxidation takes place, and this is called the oxidative addition. Okay. Now what happened that one of the PPH3 ligand actually goes out of the catalysis, so that here is actually generate a vacant site, and now this vacant site is required to acquire the double bond, or we can say the alkene. So it will coordinate first, and after that uh, hydrate transfer takes place. You can find here that one of the hydrate are actually transferred here, and it generate this type of intermediate. Okay, and now you can find here that here is also a vacant site has been generated. Now the PPH3 is initially that removed, that again come back here to fulfill the vacant site. Now what happened that now a reductive elimination takes place. Now reductive elimination has been observed between this particular group and the remaining hydrogen here. So these two will combine and do a reductive elimination, and we got our product and we got our catalyst back. And since we get our catalyst back, now this particular catalyst we again undergo the same catalytic path cycle to generate the particular alkene, or we can say the hydrogenation product. So this is the Wilkinson catalysis mechanism. We'll more elaborately discuss when we are discussing the organometallics compound, or we can say that the metal palladium mediated cross coupling reaction. Then we will discuss this in a further way. Okay. Now, rate of hydrogenation. So, as I already discussed, that Wilkinson catalysis have shown more hydrogenation over the isolated double bond, and because of the steric reason. Like here, you can find that this actually coordinate, and the PPH3 ligand and chlorine ligand are bulky enough also. So, what happened that the coordination takes place where the alkene have the lesser substituent, or we can say the isolated, so to eliminate the sterics. And that's why basically this particular styrene having the more reactivity towards the Wilkinson catalyst, whereas this particular tetra-substituted double bonds are not that much feasible. And also you can find here the cis product are more reactive over the trans product. So this thing you have to remember. And also there is certain facts is there on Wilkinson catalysis that you have to remember, that the first one is the less substituted and sterically less hindered double bond are selectively hydrogenated because of the steric issues. Also the exocyclic double bond are selectively hydrogenated over endocyclic double bond that I already also discussed. Isolated double bond are more rapidly hydrogenate over the conjugate dienes, and terminal alkynes such as are hydrogenate more rapidly than terminal alkenes. That means the triple bond have the more affinity to reduction or hydrogenated over alkenes. That is a double bond. And interesting thing is other functional groups such as the CO, CN, NO2, aryl, esters are unaffected in this particular reaction. So this shows the selectivity of this particular reaction, that only double bond getting reduced. Now we are talking about the stereochemistry, as I already discussed, that it will always show the cis addition. Because of the mechanistic pathway, we can see that it will always provide cis addition. Now where should be the hydrogenation can be attached in the above of the plane or below of the plane. This is also depend by the substituent directed group. Like here it is written that if any chelating or hydrogen bonding group present adjacent to the double bond, then hydrogenation stereochemistry is depend on the stereochemistry of the chelating or hydrogen bonding group. For example, here this is OH is there, this is a hydrogen bonding group, that is the capable of doing hydrogen bonding. So in presence of Wilkinson catalyst, irrespective of that here it might face some steric issues, however it will show the same retain the same stereochemistry upon hydrogenation, because the driving force is to this particular group, that is the capable of hydrogen bonding, and that's why the stereochemistry is exclusively matches with that particular stereochemistry. However, if the same compound, if there is a no hydrogen bonded group is there like here, then Wilkinson catalysis will follow wherever it will find less steric hindrance. So here you can find that the cis addition takes place, but here the stereochemistry is not exactly mimicked by the adjacent group. So in this particular lecture, okay, so first let us begin with the heterogeneous hydrogenation. First let me tell you that what is the actually heterogeneous hydrogenation means. Heterogeneous means that the reactant and your catalyst both are in different phase. Okay, just if you just for a brief introduction, that if you are actually seeing that a hydrogenation reaction by using palladium charcoal, then you may find that the your catalyst in the solid form, whereas the your reactant, that is the alkene, are mostly in the solvent, and the hydrogen are nothing but a gas. So basically there is a phase difference is observed between the catalyst as well as the reactant. So that's why actually it is called the heterogeneous hydrogenations. Okay, so it also have the similar properties like the homogeneous hydrogenation or similar reactivity shown. Like it is also done the synhydride addition takes place by this also. Same, the less substituted double bond reduced, less sterically hindered double bonds are more prone to do hydrogenation over the more sterically hindered bond. And also in the terms of stereochemistry, it also show directed hydrogenation in presence of a hydrogen bonded group such as the OH and NH2COOH group, and non-conjugated double bond redox in presence of conjugated double bond. This is the new something. So what should be the reaction? First, let us understand. But before that, nickel, palladium, platinum have their own significance in the heterogeneous hydrogenation, such as that if you want to reduce any alkenes over carbonyls, then you will use the hydrogen palladium, because palladium has more affinity to bind with alkenes rather than carbonyls. However, if you want to reduce or hydrogenation on carbonyl groups but don't want to reduce the alkene group, then you can use the hydrogen platinum, because platinum has the higher affinity to bind with the carbonyl group, and the affinity have their own significance in this particular heterogeneous hydrogenation reaction mechanism that I will discuss in the next slide. So as I already discussed, the heterogeneous, it is reaction between phases where the catalyst are the mostly solid in nature, and so there is a adsorption based reaction takes place where the physio absorption chemi absorption takes place. So what happened that this is the catalyst surface, and the hydrogen are come to the surface, and depending upon the active site present in the surface, it will actually show a physio absorption initially, then chemi absorption. So it will the hydro, and thus the hydrogen is absorbed on the catalyst surface, and then your olefin, or we can say that the alkenes are come here in this particular catalyst surface, or the closer proximity of this particular hydrogens to generate this particular complex. This is called the complex of alkene to catalyst. Now here this particular catalyst is palladium, and that's it is more affinity towards this particular olefin. However, if the particular reaction catalyst is platinum, then carbonyl group will get more affinity. So it will bind the physio absorption or chemi absorption takes place with the carbonyl group. However, we just restricted here because the palladium charcoal mediated heterogeneous hydrogen is much more famous. That's why actually this type of complex is generated, and the reaction is the catalyst is a just I write here that catalyst here is palladium. Okay, so palladium or co-catalyst is charcoal. So this is the catalyst, and the hydrogen absorption takes place. Then also the olefin absorption is also takes place. After that, what happened that after doing absorption, this particular hydrogen is actually inserted toward one of the carbon center to generate this type of compound. Okay, and after that, this particular uh, desorption takes place where this particular hydrogen also attach in this particular carbon center, and also due to this type of syn type of addition, the always the cis product, or we can say the syn addition of hydrogen takes place with this particular reaction. Similar thing also happen in the homogeneous hydrogenation, especially in the Wilkinson catalysis part. Okay, so there is certain example of a heterogeneous hydrogenation. However, I want to say that not only that Wilkinson catalyst are actually do this type of hydrogenation. There are certain different homogeneous hydrogenation catalysts are there, but we are not discuss those things here. We'll discuss elaborately in our organometallic courses. However, now we are back with our heterogeneous hydrogenations. So here you can find that this particular reaction is there, and first the Birch reduction takes place. Now Birch reduction is done in the electron deficient alkene, but here there is a no aromatic compound is here. That means this particular negative electron from the Birch reduction is attack in the alpha beta unsaturation. This is the 1,4 addition that I already discussed in the Birch reduction lectures. It will attack here, and this goes up, and the negative charge is generated here, and now then after taking another particular proton, here is also the initial radical came back to the, so the arrow is actually wrong here. So since it is a set mechanism, that means the arrow should be like this, then goes this, and those go via this, and after that taking another electron, it will generate the negative charge. Okay, and now this particular negative charge will go back, and here is say the methyl iodide is there, that means the alkylation takes place, and after that heterogeneous hydrogenation has been done. There is the hydrogen palladium charcoal to reduce this particular double bond to their corresponding single bond. So this is a classic example of how we actually merge the Birch reduction as well as the heterogeneous hydrogenation in one reaction. However, there is a single reaction is also there. Like here, you can find there is a exocyclic double bond is there, and this actually getting reduced. And since it is a palladium, that means the carbonyl group is not reduced; it is keep intact. And here in this particular norbordyne system, okay, what happened that in presence of heterogeneous hydrogenation, you can find here this particular double bond is more substituted and this is a less substituted. So as per the selection rule, or we can say that the facts that it will go syn addition but less substituted double bond. So the product is this. Similarly, here also, if this particular part, you can say now it is blocked. So that means the above attack is now sterically hindered. For that reason, actually, the lower addition or the endo addition takes place in the less substituted double bond. So this is the classic example of heterogeneous hydrogenations. And also there is another example of stereochemistry where the directed hydrogenation takes place. Remember that similar thing happened in the Wilkinson catalysis part also. Like here it is a hydrogen bonded group is here, and here also D2 palladium charcoal is taken to do the isotope leveling, and we can found that this particular product is generated exclusively where the stereochemistry of the addition deuterium are matches with the stereochemistry of the directed group, that is the OH. And there is some miscellaneous important examples also there, such as that cyanides are actually reduced to their corresponding amines. Azides also reduced to their corresponding amines. Nitro also reduced their corresponding amines. Okay, imines are also getting reduced to this particular thing. So this is the miscellaneous example, but yet important. Also, there are certain different type of reaction is also possible in terms of the heterogeneous hydrogenation, such as that the ether cleavage, like benzylic and allylic ether are cleaved via SN2 mechanism. So this is very important. Like sometime it is come in the question, like because the recent trend says that this type of question is repeated, that the reaction mechanism was asked. So this type of benzylic and allylic ether are cleaved via SN2 mechanism. So you have to remember this thing. Also, the CN bond cleavage can be done by using the hydrogen palladium charcoal, and cyclopropane ring cleavage is also observed. So this type of reaction you have to just remember. We are talking about the other hydrogenation reactions, especially some name reaction such as the Rosenman reaction, Lindlar catalyst, and also Raney-Nickel based reduction. So let us begin with our Rosenman reaction. So the Rosenman reaction is nothing but a chemoselective hydrogenation of a acid chloride to aldehyde. Okay, so in our lecture 11, we are actually discussing that ease of hydrogenation by using catalytic hydrogen is easier in acid chloride to aldehyde reduction, and this particular reduction can be done by using the Rosenman reduction. So what should be the reagent of that particular reaction? The reagent is hydrogen, palladium, and BaSO4. So the reaction is very simple, that this is our acid chloride, and this particular acid chloride in presence of the reagent, that is the hydrogen palladium BaSO4, and they got the aldehyde. Now you may think that why it is stop in the aldehyde, it can go to the till the alcohol part, and this is not happening because of the presence of BaSO4. So what happened, that barium sulfate, that BaSO4 is actually reduce the activity of palladium, here is the heterogeneous catalyst, due to its low surface area. So what happened that in case of any kind of heterogeneous catalysis reactions, what happened that palladium, it is having the surface because it is a heterogeneous, like it is solid, and the reactant are in the either liquid form or gas form. So what happened that as adsorption is very important in this type of reaction, and if you know a very little bit about absorption, then you must know that in any kind of surface there is a different active site presence, and depending upon the active site the physio absorption and chemi absorption takes place. Now what happened that BaSO4 here is actually acts as a catalyst poison. So what happened that BaSO4 is already blocked many of the active site of the particular palladium surface, and that's actually decrease the reduction power of palladium in order to prevent over reduction of the aldehyde, and that's why that acid chloride is reduced till the aldehyde part in Rosenman reaction condition. Otherwise it will reduct till the alcohol. Okay, so this thing you have to remember. Now let us understand the mechanistic pathway of the particular reaction. So this is the palladium BaSO4, so it generate the PdL4. So what happened that it will do the similar kind of pathway, like first the oxidatively addition takes place of this particular group, okay, and then this particular hydride transfer takes place, and then reductive elimination takes the typical reaction of the Rosenman reactions. Okay, so next talking about the Lindlar catalyst. Lindlar catalyst is a palladium based catalyst supported on calcium carbonate and modified with lead salt. Okay, so the catalyst here is hydrogen palladium and calcium carbonate and quinoline, and this particular catalyst has support by this particular CaCO3 and quinoline acts as a reaction poison or catalyst poison here. Okay, and it is selectively hydrogenates alkynes to cis alkene. It is very important that triple bond can be reduced to a cis alkene, and further reduction can possible with this particular linear catalyst condition. And the lead component poisons the palladium. There is a quinoline palladium to prevent over the ensure selectivity of the cis isomer, and also it operates under the mild condition, usually in atmospheric pressure and room temperature, and linear catalysis is widely used in organic synthesis for preparing cis alkenes. Now let us talk about the Raney-Nickel. Raney-Nickel is a highly effective catalyst that is used for the hydrogenation and dehydrogenation reaction in organic synthesis, and also it is if we cover the physical composition of Raney-Nickel, then it is a nickel aluminium alloy that has been activated by leaching out aluminium, resulting in a highly porous active form of nickel, and in this particular porous part the reaction happens. And Raney-Nickel is commonly used for the hydrogenation of alkanes, alkyne and carbonyl compounds, and also it is also employed in the dehydration of alcohol and the reduction of nitro compound. And if anyone is interested about the Raney-Nickel preparation, then they can find it on the YouTube. There is a very good video is there by how to prepare Raney-Nickel. Now Raney-Nickel can show different type of reactivity. Interesting type of reactivity. First is the alkene hydrogenation. Like if any alkene is there, then by hydrogenation it got the alkanes. Also Raney-Nickel has the capability to do benzene reduction. Now the Raney-Nickel is capable to do the benzene reduction. That is a very hard thing to do. In the ease of hydrogenation is very hard to benzene to cyclohexane reduction, but Raney-Nickel is strong enough to reduce the benzene to their corresponding cyclohexanes, and also ketone to alkanes is possible, and this is the nothing but a Mozingo reaction where the ketone is first the thiol has been generated, and after that Raney-Nickel based treatment the thiol carbon CS bond has been break and to form this type of compound, and CS bond breaking by using Raney-Nickel can be possible. Also Raney-Nickel is also capable to break the C halogen bond and CN bonds also. So it is a very stronger reducing agent, we can say. Class, we are talking about different hydrogenation reactions such as the reduction of CO group to CH2 group. This is the nothing but a deoxygenation reactions. So we are actually talking about this particular reaction where the carbonyl compound, that CO, is actually reduced to the CH2 group, certain this. And to achieve this particular transformation, there is a three different pathways there. One is the Clemenson reduction. Clemenson reduction is actually the reaction condition for the Clemenson reaction is zinc amalgam and concentrated HCl used. Another pathway is the Wolff-Kishner reduction. The Wolff-Kishner reduction is carried out via hydrogens and KOH. Also, there is a third process is there. This is called the Mozingo reaction. Mozingo reaction is actually done via thiol and BF3. So let us discuss all of the reaction in details. First, let us talk about the Clemenson reduction. Clemenson reduction is a very versatile reaction, and actually it is a reduced ketone to alkane under strong acidic condition. That's why concentrated HCl is used, and the reaction condition is zinc amalgam, zinc mercury, and concentrated HCl. The interesting thing about this particular reaction is the mechanism of that particular reaction is not clarified properly till now. Okay, but there is the proposed one mechanism is there, and that particular proposed mechanism suggests an organozinc intermediate via set mechanism. Set mechanism is single electron transfer mechanism. So let us see that what is the actually proposed mechanism. So the initially this particular ketone is there, which actually takes the hydrogen that present in the concentrated HCl is there, so H plus is there. So it will actually taking H plus and getting this type of intermediate. Now this will go a radical transformation. Basically, that is zinc actually donated one electron to the electrophilic carbon here, and we get this particular intermediate. Then this zinc are actually attached with this particular carbon to get this our organozinc intermediate, and after that this bond actually cleaves by taking the extra proton present in the medium, and we got this type of intermediate. And this will again, zinc will donate one electron here to get this a negative charge, and then this particular negative charge will take the proton present in the medium to take this, and after that zinc actually cleaved and one of the another proton is replace the zinc. So this is type of peculiar mechanism that actually given by the scientist, but it is still now not cleared, like not clarified and the verified mechanism, but there is a certain mechanism is given. Okay, so now let us talk about the second reaction, that is the Wolff-Kishner reaction. Wolff-Kishner reaction is a reaction where the carbonyl compound are getting the reduced to alkane under a strong basic condition. So in our previous Clemenson reaction, the particular reaction condition is under strong acidic condition, but in the case of Wolff-Kishner reaction, the reaction condition is the strong basic condition. Okay, so the carbonyl compound is initially treated with excess of hydrazine to get the corresponding hydrazone, which upon heating in presence of base furnish the hydrocarbon. So what should be the mechanism of that particular reaction? So initially the hydrazine are actually attached here, and after rearrangement we got the corresponding hydrazones. Then the base actually abstract this particular proton and we got this type of intermediate, and then after nitrogen elimination we got our desired alkanes here. So this is a typical mechanism of the Wolff-Kishner reaction. The third reaction that we are our topic of interest today is the Mozingo reaction. Mozingo reaction is one of the key reactions to reduce carbonyl to alkane in neutral medium. So the Clemenson is the acidic condition based reaction. Wolff-Kishner is the base media condition or base mediated reaction, and the Mozingo is the neutral medium mediated reactions. And reaction includes thiol in presence of Lewis acid, and after Raney-Nichols treatment will do the corresponding carbonyl to alkane. So the reaction is very similar. that the carbonyl are actually protected by the thiol group in presence of the Lewis acid. Lewis acid is nothing but increase the electrophilicity of this particular carbonyl compound. And then we got this type of protected carbonyl via thiol protection, we can say. And we know that after Raney nickel treatment, Raney nickel is known for the carbon sulfide bond cleavage. So Raney nickel cleave these two particular bond and replace via two hydrogen, and thus we got our corresponding alkanes from the carbonyl compound. So this is the Mozingo reaction. Now we are talking about the MPV reduction. MPV reduction says that the reduction of ketones and aldehyde to their corresponding alcohol utilizing aluminum alkoxide catalyst in presence of a sacrificial alcohol. And this reaction is a highly chemoselective and environmentally friendly metal catalysis is used here. So this is our ketone, okay, and this is our sacrificing alcohol. Now these two react in presence of aluminum alkoxide to get this type of intermediate, where the aluminum actually chelate with both of the oxygen center here, and then the alcohol hydrogen are actually transferred to the corresponding ketone carbonyl carbon, and then we got our reduction of the ketone takes place, and the sacrificing alcohol becomes a ketone, a new carbonyl compound. Now this particular path, the forward path, is called the MPV reduction, and the reverse path is the open wear oxidation. Open wear oxidation says that particular alcohol to carbonyl compound via aluminum alkoxide is called the open wear oxidation in presence of a sacrificial ketone, and MPV reduction says that the ketone or the carbonyl compound to alcohol formation in presence of aluminum alkoxide with a sacrificing alcohol. So this is the MPV reduction and open wear oxidation. The both are actually, we can say, the opposite reactions. So we'll begin with our discussion in the organometallic reagents. So in organometallic reagents, basically we are focused on 4 different organometallic reagents here. One is the grignard reagent. This is a magnesium based organometallic reagent. Then we are talking about the gilman reagent. This is the organocopper mediated organometallic reagent. Then organolithium, that lithium based, and organoboron, that boron based organometallic reagents. So we initially start our discussion with the grignard reaction. This is a very famous organometallic reagent. So grignard reagent are highly reactive organomagnesium compounds that used for nucleophilic addition to carbonyl groups, enabling the formation of alcohols. And the structure of the grignard reaction is this: RMgX, where Mg is our magnesium, X is the halogen, and R is the alkyl group. And when actually the grignard reagent react with the carbonyl compound, this R actually attacks. This R actually acts as a nucleophile, and the nature of the nucleophile is a hard nucleophile. We just look about some kind of preparation of grignard reagent, because this is something important for exam purpose and also for the general information purpose also. So how a grignard reaction can be generated in the laboratory medium? So grignard reagents are basically prepared by reacting organic halide, that is the RX, with magnesium metal in an anhydrous ether solvent, such as diethyl ether and tetrahydrofuran. And here it is also written that the reaction occurs under an inert atmosphere to prevent moisture and air from reacting with the reagent. And then after that it will form the grignard reagent. So this is the preparation reaction where the alkyl halide react with the magnesium in ether solvent to generate our grignard. And grignard reaction is actually prepared in an in situ format like. So then we are talking about the preparation of grignards. So as I already discussed, that the alkyl halide that react with the magnesium in dry ether solvent to get grignard. and it is an example of an oxidative addition, because here the magnesium is in the zero oxidation state, but in the form of Grignard reagent, magnesium is the +2 oxidation state. So it is called the oxidative addition. And since it is a -2, that means the halogen is -1, and here the alkyl group is also in -1 oxidation state. Okay. And it is the example of oxidative addition, and the X is the halide group, bromine, chlorine, iodine, and fluorine is not actually used in the Grignard synthesis. These three halogen are normally used to synthesize Grignard. And rate of addition is the 1 degree alkyl halide are much more reactive towards the Grignard synthesis over the secondary halide or tertiary halides also. And here I already discussed that this R that is actually coming from alkyl halide. So this is initially the del positive, and after getting the Grignard part, it is generating the del negative characteristics. And this R minus is acts as a nucleophile. And here a reversal of polarity observed between this particular alkyl part. Initially it is on a positive state, but in the Grignard reaction it acts as the negative oxidation state. And this is called the Ampolang reagent that we will discuss in the next slides. Here is also written the reversal of polarity observed, that is called the Ampolang system. So this is how we can prepare a Grignard. Like if there is a competition is there between bromine is also there, chlorine is also there. So bromine is much more reactive towards Grignard synthesis. So in presence of one equivalent, it will initially this Grignard has been generated, but if it is an excess, not one equivalent, if it is an excess amount, that magnesium present in the excess amount, then both side of Grignard has been synthesized. And how to store the Grignard reagent? Grignard actually stored in the inert atmosphere such as nitrogen or argon in tightly sealed dry glassware to prevent exposure to moisture and air, and they are actually kept in a cool and dark place to maintain stability. Now let us talk about the different reaction over the Grignard reaction. So in the description box I will put a handwritten notes about the Grignard reaction, so go through it. And here basically a Grignard can be react in the two different pathway. One is the acid-base reaction, and another is the reaction with carbonyl compounds. So in the case of acid-base reaction, basically if this type of system is there, ZA, so Z equal to RO, PHO, RS, RCC, RCOO, RNH2. So then it will actually, this particular hydrogen has been abstract, and it will generate the alkane, and the corresponding residue is generated. Also, alkane halides, these things are react with the magnesium and water to generate corresponding alkenes. This also reaction can be possible. This is also a side reaction. If the Grignard synthesis pathway, if there is a moisture present there, then this type of side reaction can be observed. For example, here you can see that this is the compound, and here the magnesium and water is there, or moisture is there. So basically no Grignard formation takes place, rather this type of compound has been generated. Similarly here is also the same, and in the case of 1,2 and 1,3 dihalides are not react with Grignard. So this is something that you have to remember. Next we will talk about Grignard reaction with carbonyl. This is the very important, like mostly in the exam purpose, this part is actually important for your CSIR NET GATE JAM examination. First of all, we need to learn about that Grignard. It is a hard nucleophile. Like this is the Grignard, there is the RMGX. So now this particular R acts as a negative charge, and this is actually the nucleophile, and this is the hard nucleophile due to presence of the magnesium, because magnesium is also hard. So that's why it will favor 1,2 addition product, because here you can find here this carbon in carbon, this is also in a hard center, and this is also in a hard nucleophile. So hard interaction is observed, and we got this 1,2 addition product. and this is the most normal reaction in the case of Grignard. Now there is a certain reaction is there that how a Grignard reaction, Grignard reagent actually react with different compounds. So basically, if it is react with the CO2, then it will form an acid part. If it is react with acid chloride, so two equivalent of Grignard is actually consumed in with one equivalent of acid chloride. So first R1 is actually attacked here to kick out this particular chlorine. Then it will again form carbonyl compound. So another equivalent of R1 actually attacks here to form this type of alcohol, tertiary alcohol. So this is the final product. Similarly, for the ketone, there is a one equivalent of Grignard reaction actually react to generate this type of tertiary alcohols. For the case of aldehyde, it will generate a secondary alcohol, and here is also one equivalent of Grignard reaction actually used. In ester, there is a two equivalent of Grignard reaction reagent has been used for completely react with the one equivalent of ester. First, this OR actually kicks out, and then another particular R1 actually attack to get this particular tertiary alcohol. And for the case of amides, or the Werner amides, this is called the Werner amides. So here the reaction is stopped in the ketone center, but in the case of excess Grignard reagent, then it will go to the alcohol state. Similarly, in also Grignard react with the cyano group to generate their corresponding ketones, and for epoxide, it will the Grignard is attacked from the less hindered side. So attack from here, and after epoxide ring opening, we got this type of compound. So this is the overall reactivity of the Grignard reagent. And also in the case of alpha beta unsaturated carbonyl compound, and so we know that this particular carbonyl carbon is the hard center, and this particular 1,4 center is a soft center. And since the Grignard actually yields the R minus, it is the hard nucleophile. Thus, that particular nucleophile attack in the 1,2 position, and this particular product is major, and no 1,4 attack takes place. To maintain hard-hard interaction, Grignard often show 1,2 addition. But if here this particular area, that a 1,2 addition, here if a bulky group present, such as BHA, BHD, this type of group, then the somewhat this particular addition getting hindered because of this particular steric reasons. So in that particular case, sometime 1,4 addition is felicitated, and we got this type of compound. So this is a very exceptional case, but in the case of mostly in the case of alpha beta unsaturated carbonyl compounds, 1,2 addition takes place in presence of Grignard reagent. Talking about the Gilman reagent. So in our previous discussion, that is a class 14, we are talking about the organomagnesium based reagent. Now here we are talking about the organocopper based reagent, that is the Gilman reagents. So first let us talk about the Gilman reagent. That Gilman reagents, that also known as the lithium organocopper reagent. It is written like this: R2CuLi. Are organocopper compound used in organic synthesis to felicitate nucleophilic attacks on electrophiles. They are particularly effective for a coupling reaction and the selective alkylation of various electrophile, making them valuable in forming carbon-carbon bonds. So this is the structure of Gilman reagent. This is given in your exam, R2CuLi, or sometime it is written as something like this, that RMGX and CuLi. If this thing is given in your exam, then never approach the question as a Grignard one. Remember that this composition will always give a Gilman reagent. Okay, and due to this copper present, the resulting nucleophile, that is R minus generated from the Gilman reagent, is a soft nucleophile, and it is mainly for favored 1,4 attack in presence of alpha beta unsaturated carbonyl compound. So we'll discuss in the later slides. So other form is, if it is written like this, RLiCuI, then don't treat this as a organolithium reagent. It is also a form of Gilman reagent. or sometimes written this form also. So Gilman reagent written form is different, but you have to remember that all when the copper is present there, that means the reagent is Gilman reagent. And now let us talk about the Gilman reagent preparation. There is a reagent. So in contrast to Grignard and organolithium reagent, organocopper reagents cannot be made directly through treatment of alkyl or alkyl halides. Like previously we have seen that alkyl halides are actually treated with magnesium to get the corresponding Grignard. Similar thing is observed in the organolithium base also. The organic halide react with the lithium to get organolithium, but this is not possible in terms of Gilman reagent preparation, because this particular reaction is not happen because the copper is a not strong reducing agent, and that's why they can't cleave this particular bond and doesn't replace directly. That's why Gilman reagents are made by treating one equivalent of a copper salt with two equivalent of organolithium species. So initially this alkyl halides are treated with lithium to make their corresponding organolithium compound. Now this two equivalent of organolithium react with the copper bromide in presence of ether solvent to generate the Gilman reagent. This is the R2CuLi, and this is the composition of the Gilman reagent, and lithium bromide is the salt, is the byproduct of this particular reaction. So this is the Gilman reagent. Now let us talk about different Gilman reaction. So Gilman reagent shows two different type of reaction. One is the addition reaction, one is the substitution reaction. In addition reaction, there is a two type of addition is there. One is the addition of carbonyl and another is a Michael addition. There is a 1,4 addition. Since Gilman reagent generates soft nucleophile, that's why it will show 1,4 addition. It will doesn't show 1,2 addition in presence of alpha beta unsaturated carbonyl compound. But in the case of normal carbonyl compound, it will react similar like 1,2 addition takes place. I will discuss in the next slide. And also Gilman will show another type of reaction, that is a substitution reaction, SN2 type of reaction, that will proceed this type of reaction via question answers. Okay. Now let us talk about the addition reaction of carbonyl compound. That this is the acid chloride. Acid chloride react with the Gilman reagent. Gilman reagent generates the R minus here, and that particular R minus are actually attack in the carbonyl carbon. This one goes up, this goes back, and this particular chlorine goes out of the starting material, and we finally get this particular compound. So this is the 1,2 addition product. Similarly, in the case of aldehyde and ketone also, Gilman reagent will show 1,2 addition reaction and generates this tertiary alcohol. But when the alpha beta unsaturated carbonyl compound is there, this type of thing, then Gilman reagent show 1,4 addition. That R minus will then attack here. This is because the particular copper is a soft nature and this particular center is a soft center, and this particular carbonyl carbon center is a hard center. So since the nucleophile is soft, then soft interaction takes place, and that's why this 1,4 addition felicitated here. Also, it contains certain stereochemistry, like when a directing group present in terms of 1,4 addition process, like here, this is the directing group, it is present in the above the plane reaction. So initial attack, the initial R minus, the methyl minus nucleophile attack from the backside one to eliminate the steric repulsion, and to 1,4 addition takes place, and this particular intermediate is generated. Then this negative charge goes back, and in presence of different electrophile present here, it will react here, and then this particular stereochemistry will be opposite of the initial R group stereochemistry. Like here, the methyl group attack in the lower side, and then due to the influence of this bulky group to eliminate the steric repulsion. After that, to eliminate the steric repulsion, this electrophile will have the opposite symmetry, like it will attack from the above the plane to eliminate the steric repulsion between this group and this group. So you have to remember this particular thing also. And when the directing group is not present, then this particular initial CH3 can attack either from the backward side or from the above the plane. Both the possibility is there, like here both the intermediate is generated and both the compound is observed. Both diastereomer has been observed that time. Now let us talk about some other kind of reaction. Like this particular reaction is very, very important. So here it is a triple bond is there. So what happened that methyl will attack here and this particular bond goes here and this overall group left the starting material. So we got this type of product as a final one. And also we can see here that SN2 type of reaction has been observed. Here that phenyl nucleophile will directly attack here via SN2 mechanism when the bromine kicks out and then they got the same product. Similarly, here is also a leaving group there, OTS. Similarly, that particular methyl is show a SN2 reaction, this substitution reaction, and it will generate this particular product. Today in this particular class, we talk about the organolithium reagent in brief. So first organolithium reagent has been written as like RLI, and this particular reagent is generating that R minus nucleophile, and this particular R minus nucleophile is hard nucleophile due to presence of this particular lithium. And this particular nucleophile is more harder nucleophile than grignard generated nucleophile, because lithium have the more charge density over magnesium, and that's why this particular nucleophile is much harder. Now, how to prepare this organolithium reagent? Now, organolithium reagent can be prepared via metal halogen exchange reaction, such as this is the alkyl halide. Alkyl halide react with the lithium, then the one of the lithium is exchanged with the halogen here, and we got our metal halogen product. This is the RLI. This is the nothing but organolithium reagent, and LiX. This is the salt, and the X should be chlorine, bromine, iodine. Chlorine are not used to synthesize organolithium compound, because what happened that if this is fluorine, then ortholithiation takes place. So we'll discuss in the later. Now here also this is the bromine. Here metal halogen reaction takes place, and we got our organolithium compound with LiBr. Now different reactions, like organolithium shows two type of reaction. One is the ortholithiation and one is the nucleophilic attack on the carbonyl compound. And this particular is similar like grignard, because both are the hard nucleophile. That's why both are showing 1,2 addition. Now first let us talk about the ortholithiation in brief. So ortholithiation is if there is a directing group is here, then in presence of this particular hydrogen, ortho position hydrogen has been exchanged to get this type of product. And these are the nothing but ionic type of product. This is called the ortholithiation. So which groups are actually triggered the ortholithiation process? When Z equal to OR, OCO-CH3, SO2 PH, OCO2 OMe, NMe2, CH2 NMe2, these type of groups, especially the electron withdrawing groups, these are actually shows that ortholithiation in this particular part. And this is not the final product, this is acts as an intermediate, because this particular will undergo different kind of reactions. Like here, then ortholithiated compound, this thing shows different reaction in presence of different electrophiles out there. Like this particular thing will react with any kind another alkyl halide, show a coupling reaction, something like this. Also, it will react with this type of compound as a nucleophilic addition, and we got our final product this. Similarly, this ortholithiated compound can react with the epoxide and the attack from the less hindered side, and this particular bonds open up and we got this type of compound. So it has this particular intermediate has important significance in organic synthesis. Now let us talk about nucleophilic attack on carbonyl compound. As we discussed already, that since the organolithium is generated, the R minus nucleophile, which is hard in nature, and thus this show similar reactivity like Grignard reaction. Like here, that organolithium react with the CO2 will get this ketone compound. This is the important exception over Grignard reaction, because Grignard will directly generate it to acid, but here it will generate it till the ketone part also. It will react with acid chloride. This 1,2 attack takes place and the chlorine kicks out. Initially, it will generate a ketone, and after that, a more concentration of the organolithium compound will lead to finally the tertiary alcohol. Similarly, it reacts with ketone to get that tertiary alcohol, react with aldehyde to get the secondary alcohol. Excess amount of organolithium can react with ester to get the tertiary alcohol. React with vanillapamide to get initially a ketone compound. After that, it will again go for a more reaction to get the tertiary alcohol, and cyano are also give the corresponding ketone compound, and epoxide it will show less substituted site attack, this R1, and it will epoxide opening takes place. So similar kind of reaction has been observed between Grignard and organolithium. Just this particular reaction is a exception one. It is written here that similar reactivity like Grignard reaction. Now let us give some more examples regarding the organolithium reagent. Like here, this is the product where the halogen is there. So when the halogen is present, then a metal halogen exchange reaction has been observed. So here metal halogen exchange reaction is observed, and then this particular negative charge will show nucleophilic attack to here to get our final this particular product. Also, if we add here H2O and H plus, that means acid hydrolysis, then we got only furan. This is the important reaction, you have to remember this thing. Also, if you have this type of compound, then always remember that ortholithiation takes place on the ortho position of the electron withdrawing group. Like here or here, this two is the ortho position, but since this is the electron withdrawing group present here, that's why this particular ortho position is not used, and this particular ortho hydrogen has been abstract by the or exchanged by the lithium, because there is a possibility of chelation between this particular electron withdrawing group and lithium. That's why this particular product is the final product. And here in this particular, both are the electron withdrawing group, and both ortho is this particular position is the ortho of the both NO2 group, and that's why this particular product is the major here in this particular reaction. Now let's talk about some more substitution reaction. That this is the electron withdrawing group. So here the ortholithiation takes place, and after that this particular negative charge will attack here. This particular bond goes up, this goes down, and chlorine is kicked out, and we got final this product. Similarly, here also the similar reaction has been observed, that the ortholithiation initially takes place here, and then this particular negative charge will attack a 1,2 addition with the carbonyl carbon here, and this particular negative charge will go intramolecular reaction and to kick out this particular ester part, and we got this product as a final product one. Previous discussion, we are completed all the organometallic reagents. So now we are talking about those certain different type of reagent that actually used for the epoxidation of double bonds. So initially we began with our discussion with the electrophilic epoxidation in this particular class. Then in the next class, we talking about some nucleophilic epoxidation reagents. So first of all, that oxidation of double bond, we are mainly focused on this particular reaction where the double bond or the olefins are actually in presence of the epoxidizing agents. It will generate this type of epoxides. So different epoxide generating reagents are there. So some of the electrophilic epoxidation agents, and some of the nucleophilic one. So MCPBA is one, that the metachlorobenzoic acid. MNPBA, metanitrobenzoic acid is there. DMDO dimethyl dioxidine is there. parasites are there. Parasites are nothing but this type of species where acetic acid is there. There is a one more oxygen is present there. This is called the parasite species. Then H2O2, Br2, and sulfur halides are there. Okay, so this is the structure of metachloroperbenzoic acid, and this is the metanitro perbenzoic acid, and this is the dimethyl dioxide. So in this particular class, we are talking about these four today, and in the next class, we are talking about these three. So how this is actually used for the epoxidation, because this particular oxygen center are actually electron deficient, and due to this particular thing, due to the electron deficient, this all are called as the electrophilic epoxide generating reagents. So now let us begin with our discussion with the MCPBA. So MCPBA full form is the metachloroperbenzoic acid, and this is the structure of MCPBA, and it's the electrophilic epoxidation agent. It is basically primarily used for epoxidation of alkenes. This is a double bond, and converting them into epoxides. This reaction is a selective with mild reaction condition, often in the DCM based reaction, like in the DCM solvent this reaction happens. And it is actually shows a broad substrate scope where works with a variety of alkenes, including electron-rich alkene, and strained system also shown epoxidation in presence of MCPBA. But the catch of this particular MCPBA is it causes side reaction like Bayer vinegar oxidation, like in presence of this type of ketone type of system. This will show Bayer vinegar oxidation. That means this ketone to ester formation takes place. This is the side reaction. But in the case of normal olefins, basically the epoxidation is the major one. Okay, so now we are deep down on this particular MCPBA a little bit. So first of all, let us talk about the mechanism of this particular reaction. Like all the parasite-based epoxidation can be done via butterfly transition pathway. So this is the butterfly transition. You can see that this type of transition is look like a butterfly. It is depicted here, and that's why it is called the butterfly transition. Now let us understand the mechanism in details. So this is the alkene. This actually, and this particular double bond is the electron rich, and this oxygen is the electron deficient. So what happened that this particular double bond is actually attacks here the electron deficient oxygen, and this particular bonds goes up. This particular then opens up, and this will try to capture this particular OH hydrogen here, and this bond are actually now comes here in oxygen center. So this will actually reversely attack in this particular electropositive center, and that's why it will generate this type of transition state, and this type of transition state is look like a butterfly that is actually depicted here, and this is called the butterfly transition state. And after that bond breaking and bond bond making takes place, and to generate this is our the certain product, and this is the epoxide, and this is the acid is the our byproduct of this particular mechanism. And since it is a MCPBA, then it is called it will be the perchlorobenzoic acid, metachlorobenzoic acid is the byproduct here, and this the product is generated. And in the case of peracid, like if it is a peracetic acid, then the acetic acid become side product of the particular reaction. Okay. Now, if we talk about the regioselectivity of the particular reaction, then the more electron-rich alkane have the faster reaction rate with the MCPBA, because here the oxygen is the electron deficient. So, if the alkane are electron rich, then the reaction will be much higher, or the reaction rate will be much higher. For example, here you can see that the electron donating group in presence of a alkene then it will have the higher reaction rate over electron withdrawing group. And this is reduced selectivity can be observed in these examples also. Here is a normal alkane and there is a substituted alkane is there. And this alkane are the electron rich. And due to this particular electron rich, is one equivalent of MCPBA will actually show epoxidation here, not here. So this is the reduced selective reaction. Similarly, between this isolated alkene and this particular substituted alkene, here this has the more electron rich alkene is there. So the epoxidation has been observed in this particular center only. Now let us talk about the stereochemistry. So the MCPBA based epoxidation is a stereospecific reaction where MCPBA attacks from the less hindered side. So how it is stereospecific? As we know, stereospecific means the initial hydrogens are present here at the trans. After product formation, the hydrogen are actually in trans manner. Whether it is the epoxidation in the above the plane or below the plane, the relative stereochemistry between these two particular hydrogen is always same. Similarly, if the substrate contains the cis hydrogen, so after MCPBA treatment or the epoxidation treatment, the relative stereochemistry of these two particular hydrogen is always cis in nature. So that's why it is called that it is a stereospecific reaction. And also second point is MCPBA attack from the less hindered side. So here you can find that this particular methyl are present in the above of the plane. So the MCPBA for the steric reason, this MCPBA attack from the less hindered side so that the resulting epoxide is formed in the below the plane region. Similar trend has been observed in the case of bicyclic molecule where the epoxidation will be from the less hindered side. So this is the bicycle molecule where the MCPBA, this particular conformer having the 99% selectivity and this is the 1%. The reason of this particular high selectivity is when the MCPBA attack from this side, when MCPBA attack from this particular side, so what happened, the MCPBA will actually hindered by these two particular hydrogen present in the bridgehead carbon. However, if it is come from the lower side, so this will actually getting hindered from this particular two carbon CH2 pairs present in the lower direction. So in the lower side, the steric hindrance will be much higher than the above side. So the MCPBA will attack from the above side also, and this is the more favorable attack. And the bottom phase attack is disfavored. However, if this particular CH2, the hydrogen is replaced by a bulky group such as methyl and all, then MCPBA will force to attack from the downward side, and then it is called the major product. Endo product is major in presence of steric hindrance present in the bridgehead carbon. Also, the other electrophilic epoxidation agent, this is the other paracids like peroxyacetic acid, trifluoroperoxyacetic acid and peroxybenzoic acid, out of which this trifluoroperoxyacetic acid shows higher reaction rate over these two, because this will have the very high minus I effect, which actually makes this particular oxygen is more electrophilic in nature, and that's why this particular trifluoroperoxyacetic acid shows faster reactivity in terms of epoxidation reactions. And this sphere also shows similar type of reactivity as well as the similar reaction mechanism, just like MCPBA. Also here I am to show you about that how MCPBA reacts in presence of a Lewis acid. So MCPBA with Lewis acid often undergo ketone formation. So this is the alkane system. MCPBA doesn't react with the aromatic one. So this is the alkane one react with the MCPBA to generate the initial epoxide. Now this particular epoxide is actually this oxygen lone pair has donated to the BFP. This is the and it will act as a Lewis acid, and then this type of intermediate is generated, and then loose SN2 mechanism has been observed. So this carbocation is generated, and after that this particular hydrogen transfer takes place, and then here a positive charge has been generated. Now this particular lone pair comes here to get their corresponding ketone, and this is the final product of this particular reaction. Next, we talk about the another interesting electrophilic epoxide generating reagent. This is the DMDO. This is called the dimethyl dioxidant, and dimethyl dioxidant is a highly reactive and efficient epoxidizing agent, and it is actually generated in situ from acetone and potassium peroxymonosulfate. So sometime in the examination it is given as a DMDO, or sometime it will be given the mixture of acetone plus KHSO5. So if the both is are the same, DMDO and this both are the same, okay, and also it will be must be generated fresh, because the structure of DMDO is something like this. The structure of DMDO is something like this, and this particular cyclopropane ring is also there. Also, this particular bond, this OO bond is not that much stable, so it will be can't prepare storable. So it will be generated in fresh, and it decomposes rapidly because of this particular ring rigidity as well as the weak OO bond. And it will provide exceptional selectivity, often leading to fewer side products. And also it is useful for oxidizing sensitive or functional substrate due to its mild nature. So the reaction is something like this. So I just simply rub it out. So this is our alkene system. Alkene system react with the DMDO, where this particular is the del positive, and it will undergo also a butterfly transition state, and then we got our epoxide and acetone back. So this is the typical reaction of DMDO. Today we are talking about the epoxidation of double bonds, especially the nucleophilic epoxidating agents. So initially we began with our discussion with the Br2NaOH based epoxidation. So Br2NaOH based epoxidation is reagent, sometimes written as NBS-NaOH. Basically a bromine source is required and a base is required to do this type of epoxidation. And it is a two-step reaction to generate the epoxide ring that will be discussed in the mechanistic pathway. And the very important thing is, this particular reaction is famous for the synthesis of epoxide on the more hindered side. So as I already discussed in the MCPBA based case, that the epoxide is generated from the less hindered side. But in the case of this particular reaction condition, Br2NaOH, this particular epoxide is generated the more hindered side. So this is the very key distinguishing feature between the Br2NaOH and MCPBA based epoxidating agents. And this particular reaction typically involves the formation of a bromohydrin and then followed by intermolecular nucleophilic substitution. So let us understand the mechanism first, and then we will discuss later further. So first, the mechanism of Br2NaOH mediated epoxidation, that initially that bromine are actually breaks by this particular base, and it will generate HOBr or NaOBr. Okay, so what happened then? This particular bromine is break, so this particular Br plus will actually captured by this particular electron rich olefin, and it will generate this particular 3-member intermediate. Then the OH minus present there, this will actually attacks from the SN2 pathway here, and it will be generate the bromohydrin intermediate, and after that in presence of base, this particular proton has been captured. So this particular negative charge will show a intermolecular SN2 pathway to kick out this particular bromine, and we got our this particular epoxide ring. So initially the bromine three-member ring stereochemistry is above the plane, and the resulting final epoxide stereochemistry is below the plane, and this is the actually the key feature, and that's why the particular product is generated in the more hindered side. So let us give a simple comparison between this Br2NaOH mediated epoxidation and the MCPBA mediated epoxidation. So here it is written that Br2NaOH shows more hindered side epoxidation, whereas the MCPBA yield less hindered side epoxidation. Like this particular compound is there. In presence of MCPBA, the epoxidation stereochemistry is something like this, whereas this particular Br2NaOH based epoxidation stereochemistry looks like this. This is because that initially bromine is actually attached here in the less hindered side, but after that, since SN2 type of reaction has been observed, that's why the stereochemistry getting reversed, and for that particular reason, this particular product becomes the major product. For the similar reaction here, this is the bulky group present here. So in presence of MCPBA, the lower side epoxidation takes place to avoid the steric repulsion. However, in the case of Br2NaOH, the same side epoxidation has been observed because of the reaction mechanism that I already discussed. Now let us talk about another nucleophilic epoxidizing agent. This is the hydrogen peroxide. So hydrogen peroxide is an environmentally friendly oxidant producing water as the only byproduct in epoxidation reactions. And this particular H2O2 based epoxidation is usually not stereospecific, often used with catalysts like transition metal or organocatalyst to improve the selectivity and efficiency. It will do the epoxidation, but this is not a stereospecific reaction. Earlier, like MCPBA and Br2NaOH, those are the stereospecific, but this is the not stereospecific reaction. And also, it will react with the electron deficient alkanes, especially alpha beta unsaturated carbonyl compounds. So, if you have this type of alpha beta unsaturated carbonyl compound, and if you want to do epoxidation on this particular double bond, then you can use H2O2 and OH, and the reaction mechanism is something like this. This O negative attack in here, and this particular bond goes up, and then this goes down, and this will attack in this particular electron deficient oxygen, and which kicks out this particular OH, and finally we got this type of epoxide. Now let us talk about another type of epoxidation, that is a sulfur halide mediated epoxidizing agent. Now, sulfur halide have numerous application in organic synthesis because it is actually good C1 synthon in the case of sulfur halide. Now, among them, there is a two different sulfonium halides is there. One is the sulfonium halide, and one is the sulfooxonium halide. Now, sulfonium halides are an unstable halide, and it will generate the hard nucleophile. But in the case of sulfooxonium halide, this is stable halide. And it is actually do the soft nucleophile. And due to the different nucleophilicity, this will show different reactions. For example, if you have this type of alpha beta unsaturated carbonyl compound, now in presence of sulfonium halide, since it is unstable, that's why it is a hard nucleophile. And since it is a hard nucleophile, then it will show 1,2 attack. And after 1,2 attack, then you will generate the epoxide from here, like one carbon is increased in that particular case. Like it is written here that hard nucleophile 1,2 addition, one carbon homologation takes place, and double bond keeping untouched here. And in the case by treating this same alpha beta unsaturated carbonyl compound with sulfooxonium halide, which is stable and soft nucleophile, then it will show cyclopropanation reaction. And this particular reaction is called Corey-Chaplowski reaction. And here the carbonyl group getting untouched. So if you have a alpha beta unsaturated carbonyl compound, and if you want to do 1,2 epoxidation like this type of compound, then you can use the sulfonium halide. And if you want to generate a epoxide in this particular double bond, then you can use H2O2. So thus you can do the epoxidation, hydroxylation of double bond. So in this particular class, you are mainly focused on the OS, osmium tetroxide and KMnO4 based dihydroxylation. So first of all, the dihydroxylation of a double bond that refers to the addition of two hydroxyl group across an alkene, converting it into 1,2-diol. So basically, in the previous segment, we are talking about that this react with the epoxidizing agent to generate a epoxide. Now here in this particular segment, we talk about that react with the alkene with different substrate to generate this 1,2-diol system. So basically, here the stereochemistry is not mentioned, but because sometimes there is a syn dihydroxylation takes place. Also, we are do the anti-dihydroxylation also. So for the syn dihydroxylation or the cis dihydroxylation, osmium tetroxide and KMnO4, this is a potassium permanganate has been used, which add both OH group on the same phase to the double bond. And for the anti-dihydroxylation, basically the normal method is to the epoxide generation, that initially epoxide has been generated and then epoxide has been treated with the acidic hydrolysis, that is the H plus H2O to generate the trans diol, we can say. Also, there is a name reaction also there in the pre-first method. From there also we can do the trans dihydroxylation in the double bonds. So we'll discuss in the next class, but in this particular class we are actually focused on the syn dihydroxylation using OSO4 and KMnO4. So let us talk about the osmium tetroxide first. Syn dihydroxylation via osmium tetroxide. So this is the osmium tetroxide, and osmium tetroxide is a toxic reagent, very toxic, and it always gives cis 1,2-diol. And the oxidation state of OS here, this is the 8, and this is the structure of osmium tetroxide, and the reaction is proceeded by a concerted mechanism, sometimes 3 plus 2, 2 plus 1 and 4 plus 2 reaction, out of which 3 plus 2 are most common. However, in certain cases on the certain substrate, this 2 plus 1 and 4 plus 2 is also observed. So this is the starting material. It's actually react with the OSO4 to make a osmic ester that we will discuss in the mechanistic pathway. And the KSSO3 is used to break this particular bond to generate this product. And the trans diol is never formed. So this is never formed. Only this particular product is formed. And during reaction, this osmium oxidation number change from +8 to +6. That means that OS is getting reduced and this particular double bond getting oxidized. And this particular reaction is stereospecific in nature. So now let us talk about the mechanistic pathway of that particular reaction. So mechanism. The mechanism goes via concerted mechanism. So initially what happened that this particular OSO4 react with this particular double bond via 3 plus 2 cycloaddition to form this osmate esters. And this particular osmate ester is stable and isolable. Okay. So now this is KHSO3 has been used to cleave this particular OSO bond, and then after hydrolysis and the proton taken from the solvent to get, this is our product. There is the cis diol and this is the byproduct. This is the OS6, OSO3, where the oxidation state of osmium is +6. Here is also written that oxidation number of OS changed to +8 to +6, and a reagent such as the potassium bisulfate or sometimes sodium bisulfate is commonly used to break the OSO bond and liberate the diols. So the role of this potassium bisulfate and sodium bisulfate is to break this particular OSO bonds. I hope it is clear to you. Now let us talk about the regioselectivity. First, that the reaction rate generally increases with the increasing substitution of the alkene. That means the similar kind of trend we have observed in the case of MCPBA reaction, where the alkane at the most substitute, there is a more electron density present in that particular double bond, will undergo more reaction. So here it is written that tetra substituted are the fastest, where the mono substituted is the slowest in the particular reaction. So this is the product. Similarly, in the OSO4 actually attacks from the above side to generate this particular product, and this is because to eliminate the steric repulsion, as similar of the we are discussed in the MCPBA part also. However, the same that the reaction rate generally decrease if the alkane is attached to electron withdrawing groups. Like here in this between these two particular double bond, this double bond are electron deficient and this particular are electron rich. This is electron deficient because of this particular two electron withdrawing group, and that's why OSO4 on the osmium tetroxide are actually attack here, and here these are all OS, small s. Okay, so this is the final product. And now let us talk about the stereoselectivity. So this is also a stereospecific in nature, where the cis, these two are the diastereomers, or the cis-pen twin, and the trans-pen twin, these two are diastereomer in nature, cis-trans. And after treatment with OSO4, these both are starting material, these two are final products, are also diastereomer. That means these are the stereospecific reaction, just similar like the MCPBA based reaction. So between MCPBA and OSO4 based reaction, both are very much similar, but they are shown different products. Now let us talk about the other selectivity, like in presence of adjacent group. So usually dihydroxylation that is occurs from the less hindered side, where no hydrogen bonding influence in presence of just OSO4. However, if in presence of tameda is called the tetramethyl ethylene diamine. So the structure of tameda is this, and if the tameda is present in the reaction medium, then directed hydrogen bonding has been prominent, and then directed dihydroxylation observed. Same example here, the same reaction condition, but tameda is used here. Then you can say the stereochemistry is same as the directing group stereochemistry because of the hydrogen bonding. But usually in the case of normal osmium tetroxide, it will not show any kind of hydrogen bonding. Now let's talk about the catalytic OSO4 reaction. Like OSO4 is too costly. That's why actually in practical cases, that OSO4 is not used in the stoichiometric fashion, it is used in the catalytic fashion. And in presence of a terminal oxidant, the terminal oxidant is the NMO, that is the N-methyl morpholine N oxide. What does it do actually? So after reaction, osmium tetroxide, it is initially the osmium is the +8, so it will getting reduced to +6. So then what happened, that in presence of NMO, this actually again do the oxidation of this particular OSO3 to OSO4, and then this particular OSO4 then again go via reaction pathway, and the N-methyl morpholine N oxide now become N-methyl morpholine only. So this is getting reduced, and this particular OSO3 getting oxidized, and that's why OSO4 now can be used in the catalytic fashion, where the NMO is used in the stoichiometric fashion. Here it is written that NMO oxidize OS6 to OS8, and it itself gets reduced to N-methyl morpholine. However, in absence of NMO, H2O2 can also be used as a terminal oxidant, but NMO is widely used as a terminal oxidant. Now KMNO4. KMNO4 is also capable to do cis dihydroxylation, where a treatment of alkaline with cold alkaline KMNO4 will give vicinal diol. This is a cis diol.
cis-diol. So this is also follow the same mechanism just like osmium tetroxide, like the 3+2 cycloaddition is there to form this manganate ester formation, and then in presence of base, it will actually show a cis dihydroxylation. But if the base is not present, then it will show a oxidative cleavage between something like this, and this particular bond has been break and to form this two particular diol, two particular aldehyde, and this is the side product, and that's actually decrease the yield of this particular cis diol, and that's why in the case of cis diol formation, osmium tetroxide is mostly used to do cis dihydroxylation over KMnO4. We are talking about two name reaction that is famous for the dihydroxylation reaction. One is the Woodward reaction, one is the Prevost reaction. So let us talk about the Woodward reaction first. So our topic of interest is the dihydroxylation. So there is a two type of dihydroxylation is observed. There is a cis dihydroxylation and a trans dihydroxylation. Cis dihydroxylation is observed by a Woodward reaction, and the trans dihydroxylation has been observed by Prevost reaction. So first we are talking about the Woodward oxidation, then we talk about the Prevost hydroxylation. So Woodward hydroxylation is a synthesis of syn diols or cis diol from alkane. And what is the reagent of the particular reaction? The solution of iodine and silver acetate or silver benzoate. Silver benzoate is mainly used in the Prevost. Silver acetate is mainly used in the Woodward hydrolysis, and the particular iodine and silver acetate will be in an equimolar amount. This is very, very important in the case of Woodward reaction. Okay, and in a moist acetic acid, that means in the solvent having the water content. Mostly the solvent here is used in a ethanol, and the ethanol having the water content, and this thing actually very much important to determine the stereochemistry of the diol. So what is the reaction? Reaction is basically, this is the alkane, react with the iodine and silver acetate. This is plus and minus, and in presence of the moist condition, that is we got the cis diol product. So let us understand the mechanism first, and then we look about the other stereochemistry and all. Okay, so let us talk about the Woodward reaction mechanism. So the initial attack is by the iodine. So iodine initially react with alkene, which form a cyclic iodonium intermediate. So what happened that here iodine, so this particular bond attacks in the iodine, and this goes up, and this the lone pair will goes here. So we get this type of iodonium intermediate initially. After that, the cyclic intermediate reacts with the acetate ion. So here this is a acetate ion. So what happened? This particular acetate ion actually attacks here via SN2 pathway. Okay, initially it will attack via SN2 pathway, and then a neighboring group participation is observed to remove the iodine from the substrate, and it will form a 5-member ring. And this is the intermediate of the particular reaction. After that, this 5-member ring are opened by a hydrolysis reaction. So as I already discussed that the solvent contains water. Now this particular water will attack here to undergo a hydrolysis mechanism. Just like that, initially it will attack, and this particular bond goes up, and after that hydrolysis observed. So one diol is generated, and now this particular intermediate will again initially protonation takes place, and after that again hydrolysis observed to get the cis diol product, and the particular stereochemistry of this 2 OH is cis in nature. So this is the Woodward hydrolysis. Now let us talk about the Prevost one. The Prevost hydroxylation is the synthesis of anti-diols or trans diol from alkene. So this is the alkene. This is also a similar type of reagent has been used, that initially iodine used, and then sodium benzoate uh, uh, and silver benzoate has been used with the two equivalent of amount, like the here in the case of Woodward reaction, the reaction condition both are in the same equivalent, but here the salt are actually used in the excess amount, and this excess amount will actually lead to generate this intermediate which are trans in nature, and after that the basic hydrolysis will generate the trans diol product. So let us take about the general introduction. The first, the reagent. Reagent is the silver benzoate with iodine, and in the case of Woodward hydrolysis, it is the silver acetate with iodine. But here, the silver benzoate used in an excess amount. Also, after base hydrolysis, product in the anti-dihydroxylation, that means the two hydroxyl group are added to the opposite face of the double bond. And the most important thing in the previous one is here no water or nucleophilic solvent is used in this particular reaction. So this is the very important part in the case of reversed hydroxylation. Now let us understand the mechanism first. So initially that the silver benzoate react with iodine to get this type of intermediate. Then this particular iodine will actually attacked by this particular alkene system to generate this intermediate, that is the same intermediate generated in the Woodward hydrolysis, Woodward hydroxylation. Then this particular negative charge will actually undergo a SN2 pathway to get this, and after the neighboring group participation to get this intermediate. Now this same intermediate has been observed in the Woodward hydrolysis part there, but after that in Woodward case hydrolysis takes place, but here since the solvent have no moisture content or the no water content, nucleophile are in an excess amount, the silver salt is excess amount, so this will again undergo an SN2 attack to get this type of intermediate, and after that hydrolysis takes place and it actually generates the anti-diol product. So this is the mechanistic change here, like in the case of Woodward. In the case of Woodward, you can see that this intermediate is also generated, but here the 5-member ring are opened by a hydrolysis reaction, where in the previous one, this particular 5-member ring is open via another SN2 type of attack of this particular nucleophile, and that's why the stereochemistry is changed. So this is the difference between Woodward and Prevost method. Like Prevost reaction leads to anti-dihydroxylation because it occurs in the absence of water, whereas the Woodward reaction gives syn dihydroxylation due to the presence of water or nucleophile that influence the stereochemistry. Also in Prevost method, the silver benzoate is used in an excess amount, whereas in the case of Woodward reaction, the silver acetate and the iodine are used in the same equimolar amount. And that's why in the Prevost case, second SN2 reaction allowed, and Woodward reaction that is not, because all the silver acetate are actually consumed in the particular reaction. And so this is the oxidation of alcohol. And in this particular class, we are talking about the Jones and Collins oxidation in details. So first of all, in oxidation of alcohols, there is mainly 3 types of oxidizing agent are there. One is the chromium-based oxidizing agent, and under chromium-based oxidizing agent, there is a Jones reagent, Collins reagent, PDC, PCC, and PFC are there. In the case of Mn-based oxidizing agent, MnO2, MnOACO2, and Ba2MnO4 is there, out of which the MnO2 are the most important in the manganese-based oxidizing agent. And also there is a DMSO mediated oxidizing agents are also there, out of which is the Swan oxidation, Kodekim oxidation, Moffat-Pitzer, and many more oxidation are there in the DMSO mediated oxidizing agents. Okay, and there is other reagents are there as well. So basically, oxidation of alcohol, what is the meaning of oxidation of alcohol? Oxidation of alcohol means that alcohol initially transferred to aldehyde and followed by more oxidation. It is coming in the acid. So this is the overall scenario of our oxidation of alcohol. So let us begin with our discussion with Jones reagents. So it is the chromium based oxidation, then the Jones oxidation. The combination of CrO3 and sulfuric acid is often referred as Jones reagent, and the oxidation of alcohol with this particular reagent in acetone solvent is called the Jones oxidation. So this is the typical reaction. Like Jones reagent, this is the alcohol. Now in presence of Jones reagent in 0 degree temperature, it will become aldehyde. However, in the room temperature, Jones reagent shows uncontrolled oxidation where the particular alcohol is directly converted to their corresponding acids. So here it is written that in room temperature, Jones oxidation shows uncontrolled oxidation. That means that directly alcohol to acid transfer takes place. However, in low temperature, it will show controlled oxidation. And since this particular reagent, Jones reagent, contains sulfuric acid, that's why this particular Jones reagent is not useful in presence of acid-sensitive functional groups. This is a very much important thing that you have to remember that thing. Okay, so now let us understand the Jones oxidation mechanism. So first of all, let us understand the reagent. The reagent of Jones oxidation is CrO3, chromic trioxide, and H2SO4, or K2Cr2O7 plus H2SO4 is also used as a Jones oxidation. Now in aqueous acid, CrO3 forms chromic acid, which oxidizes the alcohol to the carbonyl compound. So let us see the mechanism first. So initially, this is the chromic acid that is generated in presence of H2SO4. Now what happened, then this particular oxygen lone pair will attack in the chromium, and then it will do a certain rearrangement to get chromate ester, and it looks like this intermediate. So after that, what happened, that this one of the oxygen is actually captured this particular hydrogen here, and then this particular bond goes there, and the particular chromate ester breaks apart, OCR bond breaks apart to get this particular ketone compound, and this H2CrO4 is the byproduct. And interestingly, Jones reagent is only be able to oxidize an alcohol if it contains at least one hydrogen here. That means tertiary alcohols are not undergo oxidation in presence of Jones reagent. And we can easily explain that particular thing via this particular mechanistic pathway. And if the initial starting material is primary alcohol, then it will be after oxidation, it will be either aldehyde or acid, depend upon the reaction condition temperature. But if it is a secondary alcohol, then it is always generate ketone, and in case of tertiary alcohol, no reaction takes place, that I already discussed. Now let us see about some examples. Here it is a alcohol is there, secondary alcohol is there. Now in presence of Jones oxidation, it is form a ketone. Similarly here also, this is a secondary alcohol. In presence of Jones oxidation, it will generate their corresponding carbonyl compound, that is ketone. Now let us talk about another particular interesting example, that is another chromium based oxidation. This is called the Collins reagent. Collins reagent is a moisture sensitive reagent, and it is actually controlled oxidation shows because it is a less reactive than Jones reagent. And here, if you see here, the composition of Collins reagent contains CrO3 and pyridine. There is no acid content is there, and that's why the acid sensitive functional group are tolerates in this reaction condition. And this is the structure of Collins reagents. This is the structure of Collins reagents. Now let us talk about certain example. The reaction mechanism is similar, just like the Jones reagent, and the reaction is basically, it is also requires at least one particular hydrogen to do the particular transformation. So the Collins reagent also unable to oxidize the tertiary alcohol. So here you can find that this is the alcohol, secondary alcohol is there, so it will reduce to their corresponding ketone compound. And also this type of epoxides containing alcohol are also getting oxidized to their carbonyl compound without breaking the epoxide ring. But in the case of Jones oxidation, what happened? That this epoxide might possibility of breaking, because this particular lone pair will attack in the hydrogen or the proton source in the reaction mixture. But in the case of Collins reaction, that thing doesn't happen. So today we'll discuss PCC and PDC. So first let us talk about PCC. So PCC is nothing but, the full form of PCC is pyridinium chlorochromate, and this is the mixture of some reagent like CrO3 and HCl and pyridine. And the composition of the reagent is something like this, where this CrO3 react with HCl, and then one of the proton actually taken up by this particular pyridine, and it makes like this type of ionic complex. So what is the general introduction of the particular PCC reagent? That first, it is not a moisture sensitive reagent. Like in the case of previously, Jones and Collins both are moisture sensitive reagent, and this is the not a moisture sensitive reagent. Also, since this type of composition is there, so that's why reagent composition acts like a buffer solution, and it shows control oxidation. For example, it will directly take this particular alcohol to their corresponding aldehyde. No acid group transformation takes place. Also, PCC has a interesting reaction role, where oxidation of tertiary allylic alcohol is done by PCC, and this type of reaction is called the Babler oxidation. So this is the tertiary alcohol, and there is the allylic position is there. So it is a tertiary allylic alcohol, and PCC actually able to do this type of tertiary allylic transformation. Here you can see. And also this reaction is carried out by a 3+3 sigmatropic reaction. It is a regioselective reaction, because here like in allylic position, it needs one hydrogen to proceed that particular reaction, and we can easily understand this particular thing via the mechanistic pathway. So now let us talk about the mechanistic pathway in details. Babler oxidation mechanistic pathway. So initially this particular PCC part is actually initially attached with this particular OH, so make this particular thing. Now you can see here, this is 1, 1, this is 2, this is 3. Similarly, here is also 2, and this is also 3. So that means a 3,3 sigmatropic transformation is observed here, and this particular bond breaks apart and this particular bond is generated. So this type of intermediate is generated. Now after that, here as the oxygen actually attached here you can find here it is there is a one hydrogen is there, and this particular hydrogen is very important, because now this particular chromium part will capture this particular hydrogen, and the corresponding ketone has been generated. And this particular mechanistic pathway is proved via isotope leveling effect. That means the mechanism is verified. Now let us talk about PCC some examples. PCC based some examples. So here you can find that this is your ketone. First, it is treated with Grignard reagent. Grignard reagent treated means that methyl is entered here, and it will generate an alcohol. So that means this is looking like a tertiary allylic alcohol, and then PCC is there. That means the Babler oxidation takes place, and the final product is this. And this is it is your homework to do the mechanistic pathway in your home. Okay. Similarly, here also very interesting example is there. Like here you can find that there is no tertiary allylic alcohol is there, but this is a cyclopropane ring. This is the prone to break. So that means that it will show a ring expansion reaction, and ultimately it will also show Vabler oxidation, but in a different mechanism, and this mechanism is also your homework. Now let us talk about the pH dependency of PCC. So the composition of PCC says that it is have the acid part also as well as the basic part also. However, the pyridine is not that much basic that actually neutralize the HCl completely. That's why the PCC becomes slightly acidic, and that's why sometimes buffer has been used, and the buffer is normally the sodium acetate. Sodium acetate as a buffer has been used uh, to make this particular thing on basic. So here you can find that in normal PCC condition, this will show cyclization product. However, in basic condition, this type of excess H plus is not present in the reaction medium, and that's why this only this oxidation has been shown, and double bond keep intact. So this is a very interesting observation. So you have to look about it. Next, we are talking about the PDC. PDC is pyridium dichromate. It is a neutral oxidizing agent, and this is the structure of pyridium dichromate. So here, this is the main reacting partner, and also there is a pyridine is there, acts as a counter anion, you can say, because this particular O are prone to be O negative. Okay, so that is not the main issue. This is our overall reactant or the reagent, and it is a neutral oxidizing agent, and here is no acid is there. That's why it is a not acid sensitive reagent, and interestingly that it is shows solvent effect. Now this particular thing we'll discuss in later slide. Now here we can say that how PDC actually work. Like PDC will show the similar oxidation trend like PCC. This particular secondary alcohol will be transferred to their corresponding ketone compound, and similarly here also same transformation has been observed without altering these double bonds, exocyclic double bonds. Okay, so now let us talk about the solvent dependency. So this is the alcohol. If PDC is treated with DCM, then control oxidation has been shown. However, if the PDC is actually present in the DMF solvent, then uncontrolled oxidation is shown. That means that in DCM solvent, the oxidation is restricted till aldehyde, but in case of DMF solvent, the oxidation is tends towards acids. And this type of solvent effect is primarily observed due to the solubility and reactivity in different solvent. DCM is a polar solvent. Polar solvent increase PDC dissociation and solubility, enhancing its reactivity and oxidation rate, as well as the non-aqueous solvent like DCM. Like in the case of DCM, there is a little no water content is there, and that's why actually it helps to control selectivity. But in the case of DMF contain water content, and that actually coordinate with the chromium species, which influencing this oxidizing strength, and that's why this particular uncontrolled oxidation has been. So in our previous discussion, we are talking about the PDC and PCC based oxidation reactions. Now in this particular part, in the last segment of our chromium based oxidation reagent, and here we are talking about the PFC and ETERD reaction. So first let us talk about the PFC in details. PFC's full form is pyridium pseudochromate, and it is a mild oxidizing agent for the primary and secondary alcohol, and the compounds with acid sensitive group can be oxidized without buffering the reaction mixture. Because of that, it is a mild oxidizing agent, and no acid direct acid content is there. And also PFC can oxidize activated CH bonds. So now let us talk about that how that particular reagent PFC is generated. PFC is generated by treating with CrO3. HF and pyridine. When react, we get this type of composition, and this is the composition of PFC. And PFC will show control oxidation for primary and secondary alcohol. So this is the primary alcohol. Primary alcohol is generated after PFC treatment. It will generate aldehyde, and in the case of secondary alcohol, it will generate ketone. For example, here you can find here that I already discussed that PFC can also oxidize activated CH bond. So here in the presence of PFC, this oxidation takes place. So it is a very interesting example. And so you have to remember that thing. Also, as I already discussed, this PFC in presence of secondary alcohol generate ketones. So you can see here. And also CH activation here is also done, like PFC in an acidic condition corresponding aldehydes. Now let's talk about our last segment, is the Etard reaction. Etard reaction suggests that the direct oxidation of an aromatic or heterocyclic bound methyl group using chromyl chloride. So here the reagent for Etard reaction is the chromyl chloride, and the solvent is fairly DCM. It's mostly used. And what should be the mechanism of this particular transformation, methyl to CHO? Basically, it proceeds through a formation of a chromyl ester intermediate during the reaction that we'll discuss in our mechanistic pathway slide. And it is the common method to oxidation of toluene to benzaldehyde under mild condition. So this is an important reaction. So now let us talk about the mechanistic pathway. So mechanism is little bit tricky here. So what should be the mechanism? That initially a in reaction is generated. So this particular this particular bond as goes here, and this particular double bond is actually attack here chromium center, and this oxygen bond is opens up. So this type of intermediate is generated, and this particular oxygen are actually capture this hydrogen here to make this intermediate. And after that, you can find here that this is 1, 1, 2, and this is 1, 2, 3. So that means that 2, 3 sigmatropic rearrangement takes place here. That the similar thing that is observed in the case of Babler oxidation also, where is the 3 plus 3 sigmatropic reaction. But in the Etard reaction, 2, 3 sigmatropic rearrangement is observed. And after doing 2, 3 sigmatropic rearrangement, this type of intermediate is generated. Now, in presence of base or in presence of intermolecular chlorine here, it will actually capture the hydride here, and then this particular bonds goes here, and the particular rest of the chromium part goes out of the mechanism, out of the reaction mixture. And then we finally found this type of aldehyde, benzaldehyde. So what should be the limitation? The limitation is that with this particular reaction condition, multiple product formation possible depending upon the starting material or the intermediate is generated. So this is the main issue of talking about the manganese mediated oxidation reagent such as MnO2 in details. So first let us talk about the MnO2. There is a manganese based oxidation. MnO2, it is a heterogeneous suspension of active manganese dioxide in a neutral medium. It can selectively oxidize, and the important and the notable thing is that MnO2 is used to oxidize allylic, benzylic, propoxylic and other activated alcohol to their corresponding aldehyde and ketone. This is very, very important, this highlighted point. Like MnO2 is only to allylic, benzylic and propoxylic activated alcohols to their corresponding aldehyde and ketone. And hydrogen bond donor solvent, laserized polar solvent, has been shown to exhibit a strong deactivating effect, perhaps due to competition with the substance. This is not that much important. Like this particular line is very important for the MnO2 synthesis. Now let us talk about how to prepare this activated MnO2 complex. Like activated MnO2 can be obtained by the oxidation or reduction reaction of potassium permanganate KMnO4 with a Mn2 plus salt such as MnSO4 under either alkaline or acidic condition, followed by through drying. So basically a redox reaction has been performed to generate the MnO2, where the particular KMnO4, potassium permanganate, is treated with Mn2 plus salt, as a manganese sulfate, uh, in water or alkaline condition to get this particular MnO2, which is our activated reagent here, and H2SO4 and K2SO4 is the byproduct of this particular reaction. So how the MnO2 actually react? So basically, you can find here in this particular example, this particular alcohol is a allylic alcohol because the double bond is here, and this particular center is the allyl, and this particular OH is here. So this is called the allylic alcohol. So in presence of MnO2, just this allylic alcohol are actually converted to their corresponding aldehyde because it is a primary alcohol. So it will convert aldehyde. If it is a secondary one, then it will be shown in the ketone. But in the tertiary won't react with MnO2. So for understanding that why this type of activated alcohols like allylic, benzylic, propazylic are actually react with MnO2, let's dive down into the mechanistic pathway. So initially in solution phase, this alcohol, this is the normal alcohol, we can say that this lone pair of oxygen is actually donated to the Mn to generate this type of complex, and this complex is generated in the manganese surface. After that, what happened, that a radical pathway is observed. So this particular CH bond cleavage takes place. Similarly, these oxygen bonds are also cleavage takes place, and it will generate these two radicals. Now, depending upon the stability of this particular radical, the reaction proceed, and this is the rate determining step, we can say. Now, as we know in the radical chemistry course, I have already discussed that allylic, benzylic, propazylic case, this particular radical is much stable. So if the R here is either allylic, benzylic or propazylic, then the stability of this particular radical increases manifold, and that's why that Mn will this manganese type of reagent are actually able to do this type of transformations. For here it is written that allylic and benzylic radical are resonance stabilized, and that's why selectivity towards the allylic and benzylic alcohol oxidation is increases manifold in presence of MnO2. Okay, so here it is also written that the allylic benzylic selectivity occurs because the analogous radical intermediate, this is this particular intermediate, this is very important, is in the oxidation of alcohol that is not allylic or benzylic. Like if it is not a allylic or benzylic alcohol, then formation of this radical, this bond cleavage is very less, and that's why this type of reaction selectivity will decrease. So if it is an allylic, benzylic or propazylic radical, then only this type of cleavage observed and this radical is generated. So now what should be the next step? So in the next step, in the rapid final step, that Mn3, this is the Mn3, Mn3 is reduced to more stable Mn2. Like Mn2 is the most stable, where Mn3 is the least stable. So this type of homolytic cleavage is observed. Like this particular bond breaks apart and this also breaks apart. So this CO bond is formed via radical pathway. So double bond is formed to give the aldehyde product, which is washed away from the oxidant solvent by the solvent. So as this particular bond cleaves apart, the corresponding aldehyde are actually removed from the Mn surface and go to the solution state. So this is our final product, and this will be our side product is there. Okay, so I hope this mechanism is clear to you. Now let us deep down some kind of example. So here you can find that this particular starting material contains two different type of OH. So this is the benzylic OH and this is the normal primary OH. So as I already discussed that in the case of MnO2, benzylic radical is generated here, which is much more stable due to the presence of this particular pH group. That's why that this selectivity towards benzylic alcohol to ketone generation is much more facile here, and that's why this particular OH is actually oxidized, and this will this red OH remains intact. Similarly, in the next example, you can find this particular OH is much activated OH because of this two particular triple bond. This is a propoxylic OH. So this will also actually in presence of MnO2 selectively oxidized to their corresponding ketone compound. Also in the third example, you can find here that this is also a OH present in the benzene ring, and this particular OH is also there, which is present in the benzylic position. As we already discussed that MnO2 is actually oxidized in the benzylic, allylic and propoxylic position OH. So this will getting selectively oxidized to their corresponding carbonyl compound. In this particular class onwards, we started with the DMSO mediated oxidation. So first of all, let us talk about the DMSO. DMSO is the dimethyl sulfoxide and the structure is something like this. Okay, and this DMSO can be activated by reacting with different electrophilic reagents such as oxyl chloride, dicyclohexyl carbonamide, sulfur trioxide, acetic anhydride, and N-chlorosuccinamide. So this particular DMSO is activated by this type of reacting with this type of electrophilic reagent, and then the activated DMSO will responsible to react with certain primary or secondary alcohols to get their corresponding carbonyl compounds. Now, depending upon this different electrophilic reagents, the DMSO based oxidation have different name oxidation, like Swan oxidation, Pfister-Moffat oxidation, Komblum oxidation, Parik-Doing, Korekim, and Albert-Goldman reagents. So these are the same DMSO based oxidation. However, the electrophilic reagents are different in the case of different name reactions. So before entering the name reaction, first let us understand the general mechanism that how DMSO getting activated, and it will react with the alcohols to generate their corresponding aldehyde or ketone compounds. So this is the general mechanism of DMSO based oxidation. So this is DMSO, and this is the electrophilic reagents. So what happened that these two actually react to generate this type of species, and this is called the activated DMSO compound. Now this activated DMSO compound is getting nucleophilic attack by this particular alcohol. This O contains the lone pair, and this lone pair will get attacks here. This is the electrophilic center now, and it will generate this type of intermediate. And this intermediate is very much important. After that, in presence of base, basically one of the hydrogen abstraction takes place from the sulfur, and it will generate a ylide system. And now this ylide will actually captures the adjacent proton, and then finally the intermediate breaks down to generate the corresponding carbonyl compound and dimethyl sulfide as a byproduct. So this is the general mechanism of DMSO based oxidation. Now also there is certain a certain possibility to generate some side reactions, like methyl trimethyl ether formation can occur as a side reaction. Basically what happened that this ylide is directly getting nucleophilic attacked by the alcohol to generate this type of methyl thiomethyl ether formation, and this type of side reaction is called the Pumera rearrangement. Okay, and this thing actually observed when the then this type of side reaction has been observed. Also, if the reaction medium deprived of base, then there is a reverse reaction is also possible. Basically, this intermediate is generated. After that, this particular leaving group will get SN2 attack here to break this particular intermediate and getting our DMSO back, and we got this new product. So this is also a possibility of DMSO based oxidation. So now let us talk about Swan oxidation in details. So Swan oxidation, the reagent is similar like DMSO, and the electrophilic reagent here is the oxyl chloride, that's COCl2, and base here is triethylamine. Now Swan oxidation can do primary alcohol to aldehyde and secondary alcohol to ketone, and no tertiary alcohol getting oxidized here, because in the mechanistic path, as I already discussed, that this alpha hydrogen is required for generating the carbonyl compound. So tertiary alcohols are not getting oxidized. And also it is a convenient method for the production of DMS chloride intermediate without using DMS and chlorine. So this is the fact we can say. And so this is the reaction. Basically here you can find that the secondary alcohol is here. Now in presence of Swan oxidation condition, this alcohol will getting converted to their corresponding ketone compound. Okay. So now let us talk about the mechanistic pathway of the particular reaction. So what happened that the DMSO getting activated by reacting with the oxyl chloride, that is COCl2. Now this particular negative charge will attack here, and then this chlorine getting left, and then after that this chlorine attacks here in the sulfur center, and after that chlorine attacks here in the sulfur center, and this particular bond breaks down, and after the decarboxylation and decarbonylation reaction takes place, rearrangement takes place. So finally we got our this intermediate, and this is called the activated DMSO compound. Now this is called the activated DMSO compound. Now the alcohol present in the medium getting attacked by a nucleophilic addition takes place to generate this intermediate. After that, the chlorine has actually captured the excess hydrogen here, and to get this particular intermediate, then base come into the picture, and then base captures this particular hydrogen to generate the ylide system, and then this particular ylide will actually captures the alpha hydrogen here, and then particular intermediate breaks apart to generate our corresponding aldehyde. Because it is a primary alcohol, so it is generate aldehyde and SME2 as a byproduct of this particular reaction. Now, in terms of Swan oxidation, aliphatic long chain alcohol can be oxidized. Aliphatic long chain alcohol can be oxidized, such as this is the aliphatic long chain, and in the Swan oxidation condition, this will also getting oxidized. Also, oxidation of alcohol in presence of sulfide, sulfur are not oxidized. Like if the particular compound contains sulfur as well as the oxygen, then only this particular oxygen's alcohol center getting oxidized, sulfur center is not getting oxidized. Also, since this is not acid sensitive, acid is not present in the reaction mixture, so acid sensitive functional group also getting tolerance. So here is the allylic alcohol is there and the normal alcohol is there. Both are oxidized to their corresponding carbonyl compound in presence of Swan oxidation conditions.
Only focus on Korekim oxidation and other DMSO mediated oxidations. Okay, so first we begin with our discussion with Korekim oxidation. So this is the Korekim oxidation. So Korekim oxidation is an organic reaction that converts primary and secondary alcohol to aldehyde and ketone using N-chlorosuccinamide and dimethyl sulfide under mild non-aqueous condition. So if you remember the particular reaction mechanism of DMSO mediated oxidation, then you will find that there is a one electrophilic reagent is there which actually activates the DMSO. So, and depending upon the electrophilic substituent, the oxidation name change. Like for Swan oxidation, the electrophilic reagent is COCl2.
Here it is the N-chlorosuccinamide. And why this codechem oxidation is important? Because this particular codechem oxidation is highly chemoselective in nature and it is tolerates sensitive functional groups. And this is the particular reaction. So here you can find that this is our secondary alcohol. Now here codechem oxidation is the NCS and dimethyl sulfide is here. Here DMSO is not used. Here dimethyl sulfide is used, and this dimethyl sulfide will getting activated by NCS. So we will discuss in the mechanistic pathway in the next slide. So however that this will activated and then the similar mechanism has been followed like Swan oxidation. So you can find here that this particular secondary alcohol which is selectively oxidized to their ketone form, and all the other functional group are keeping intact. So it is a highly chemoselective in nature, and after that it will go via certain transformation to get a natural products. Okay, so now let us discuss about the mechanistic pathway of codechem oxidation. So as already we discussed about the previous Swan oxidation part, the DMSO mediated oxidations are followed in a certain pathway. Similarly here it is not a DMSO is used here. Here dimethyl sulfide itself is used. Now this will actually attack with the react with the N-chlorosuccinamide here present, and then this particular structure is generated, and then this particular lone pair of nitrogen will attack here and the chlorine moves out and we got our activated DMS compound. Okay, now after the second step, this alcohol, whether it will be primary or secondary, so this particular O contains the lone pair. That lone pair actually attacks here and remove this particular part from this system, and we got this our intermediate, and this intermediate very famous, as I already discussed multiple time about this particular intermediate. And after that the base will actually captures the hydrogen from here and generates a ylide system. This is a sulfur ylide system. Now this particular negative charge will captures this adjacent proton here, and then this particular bond goes here, and this particular DMS removed from the from the structure. So finally we got that this is the elevated step here. So this will ylide formation takes place, and then this particular rearrangement takes place. Not rearrangement, this hydrogen is abstracted by this particular negative charge, and this bond goes here, and the oxygen sulfur bond breaks apart to get our corresponding aldehyde compound. Since it is a primary alcohol, so aldehyde will be the major. If it is a secondary, then ketone will be the major product, and we got our dimethyl sulfide back. So this is the mechanistic pathway of the codechem oxidation. Now let us talk about the Parik-Doing oxidation. Parik-Doing oxidation is nothing but another DMSO based oxidation. Okay, and this is also done the same part, but here the interesting thing is electrophilic reagent is changed. Now the electrophilic reagent is here, it is used sulfur trioxide and pyridine combination is used to activate the DMSO. So here you can see this particular example. This is the primary alcohol. Okay, so rest is not that much important for us right now. So here it is the SO3 DMSO pyridine. So it will activate the DMSO, and after the triethylamine what will do? It will abstract the proton and make this ylide, and then we got finally this primary alcohol converted to aldehyde. Okay, and this is actually useful for the large scale synthesis or large scale reaction, because this particular method has the ease of workup, and it will do under a near ambient reaction temperature. When the room temperature reaction happens, and that's actually made it suitable for doing large scale synthesis. So here is another example. You can find here that this particular is the primary alcohol. In presence of this particular reaction condition, there is the Parik-Doing oxidation reaction condition. So it will generate their corresponding aldehyde. Now let's talk about another particular DMSO mediated oxidation, that is the Pfizer-Moffat oxidation. And this particular DMSO based oxidation is actually first reported in literature. Okay. And here the electrophilic reagent is DCC, dicyclohexyl carbonamide. And this is acts as an electrophilic activating agent with a bond state acid prompter to activate the DMSO. And this is also a room temperature based reactions. So this is the example of the Pfizer-Moffat oxidation, where basically this is our the secondary alcohol present here. In presence of DMSO and DCC, it will generate the corresponding ketone compound, and these groups are keeping intact, or no reaction happens with these particular groups. Okay. However, there is a certain problem with this particular reaction, especially by using with DCC. Like carbonamides, that the DCC is actually yields water soluble byproduct, so isolation would be a difficult task for that particular reaction condition. So that's why instead of DCC, EDC was used. So what is the full form of EDC? EDC is 3-dimethyl aminopropyl 3-ethyl carbonamide hydrochloride. So this is the EDC. So this particular can be used to eliminate the removal of byproduct problems, like this is generates the water soluble byproduct, so isolation can be difficult, but by using EDC the isolation getting easier. So let us understand the structure of EDC and DCC first. So first it is the EDC. So EDC is looking like this. So that is not that much important, but you can check out. And the DCC structure is this, dicyclohexyl carbonamide. So now let us check about some examples of Pfizer-Moffat oxidation. So this is the example. So you have to find that this is the secondary alcohol present here, and it will generate their corresponding ketone. So I hope that it will be clear for you. Now let us do a simple summary of DMSO based oxidation. Like till now we have learned about 6 DMSO based oxidation. So just we check about the reaction condition as well as the electrophilic reagent first. So first we have learned about the Swan oxidation. The reaction condition is DMSO, COCl2 and triethylamine, and the electrophilic reagent in Swan oxidation used, it is the COCl2. Then we learn about the Korekim oxidation. Korekim oxidation, the reaction condition is dimethyl sulfide, not dimethyl DMSO, and N-chlorosuccinamide and triethylamine, and here the electrophilic reagent is NCS. Then we learn about the Pfizer-Moffat oxidation, where DMSO, DCC and triethylamine is used, and the electrophilic reagent is either DCC or EDC. Then it is come to the Komlam oxidation. DMSO, RCH2Br is used as the electrophilic condition, and the triethylamine. Then Parik-Dewing oxidation. Parik-Dewing oxidation we discuss, where the SO3 and pyridine has been used as electrophilic reagent, and this is a useful condition for a large scale synthesis. And then the Albright-Goldman reagent, where the electrophilic reagent is used, that is the acetic anhydride, and the reaction condition is dimethyl sulfoxide, acetic anhydride and triethylamine. Of alcohols, and here we talk about some unusual oxidative reagents. So in this particular class we talk about metal based oxidation, then we talk about some radical based oxidation reagents, and then hyperpresent iodine based oxidation reagents. So we begin with our discussion with the metal based oxidation reagents. So the metal based oxidation reagent is a tetra N propyl ammonium perruthenate. There is a TPAP based oxidation, and the structure is this, and here the ruthenium metal is present here. So ruthenium tetroxide is the RuO4, and to a lesser extent the perruthenate ion, that is the RuO4 minus, where the oxidation state of ruthenium is 7, are powerful than rather non-selective metal oxidants. This ruthenium tetroxide is a very powerful metal oxidants which actually oxidize to alcohol to acid. However, here we talk about the TPAP based oxidation. Now this TPAP based, due to the presence of this tetra N propyl ammonium part, which is written here, that perruthenate salt with large organic counterions. So this is the large organic counterions. There is the tetra N propyl ammonium. So this provides to the mild and selective oxidation in variety of organic solvent. So as I already discussed previously, that ruthenium textile is a very vigorous oxidating agent. It will directly oxidize alcohol to acid. But presence of this first the pyrruthenate ion, where the ruthenium is +7 oxidation state, and presence of this particular bulky organic counter ion part, the selectivity of ruthenium tetroxide and the selectivity will increase and reactivity will decrease. So this actually stop oxidation of alcohol to their aldehyde for the primary one, and the secondary one it will be stop as the ketone. But if we add direct RuO4, then what happened, that it will directly for the primary alcohol it will directly convert it to acid. Okay, that's why this particular large organic counter ion is required. Also, it is written here that in conjunction with the stoichiometric oxidant such as the N-methyl morpholin N oxide, is the NMO that actually used in the OSO4s also. TPAP oxidation are catalytic in ruthenium and operate at room temperature. That I already discussed. If you remember, then osmium tetroxide OSO4 based reaction where the cis dihydroxylation occurs. So there also NMO is used, so that OSO4 used as a catalytic amount. Here also NMO is used, so that this particular will become used as a catalytic amount. And that's actually signifies that this is also a redox reaction takes place in the ruthenium part. So that we'll discuss in the next slide. Okay, and these reagents are relatively non-toxic and non-hazardous in nature. Now there is a reaction here you can find that this is the primary alcohol. Now in presence of TPAP, NMO and DCM is a solvent here. It will generate their corresponding aldehydes, and here also molecular shifts used. Now to achieve the high catalytic turnover, since as I already discussed that in the presence of NMO, TPAP is actually used in the catalytic amount. So there is a catalytic turnover is there. So that catalytic turnover means that how many catalytic cycle can be performed by the catalysis before it getting deactivated. So this particular improve the catalytic turnover, more the catalytic turnover, more the catalysis efficiency. So addition of powder molecular shifts to use to basically remove the water that is generated during the reaction. So this particular catalytic turnover getting increased, and that's why molecular shift has been used here. Okay. So the following oxidation state change has been proposed to occur during the reaction that I already discussed, that since the NMO is used, that means that ruthenium side there is the oxidation reduction takes place. So what happened, that ruthenium 7 is the initial condition, it gets 2 electron to get ruthenium 5. Now this ruthenium 5 will undergo disproportional reaction to generate ruthenium 6 and ruthenium 4, and ruthenium 6 will get 2 electron to get ruthenium 5. So this is the catalytic cycle was done in this particular reaction conditions. Now let's talk about N-oxonium mediated oxidation. Now N-oxonium salts are mild and selective oxidant for the conversion of primary and secondary alcohol to corresponding carbonyl compound. Okay, and these oxidants are actually unstable and generated in situ in a catalytic cycle using a stable stoichiometric oxidant. So this is the N-oxonium salt. Okay, now it's react with the alcohol, either it is primary or secondary. So here it is a secondary alcohol. So react with get this particular byproduct and our corresponding ketone. Okay, and this particular N-oxonium salts can be prepared by oxidation of a nitrile radical or hydroxylamine. So here also we can say that since this is formed by a radical pathway, then we can say that tempo will be a good successor of this particular enoxonium formation. So 2,2,6,6 tetramethyl 1-pyrimidinyl, that is a tempo which catalyze the oxidation of alcohols to aldehyde and ketone in presence of variety of stoichiometric oxidant such as MCPBA, sodium hypochlorite, that is NaOCl, bis acetoxyioidobenzene. These all are the oxidants. So what happened at tempo in presence of acidic condition, it will generate the N-oxonium oxonium. Okay, so then this will actually used to oxidation of primary and secondary alcohol to their aldehyde and ketones in the presence of this type of stoichiometric oxidants. So here we will discuss some examples. So here in this particular structure we can find that this is the OH, the primary alcohol here. Now here tempo is used and the oxidant here is used the NaOCl. Okay, so it will actually convert to their corresponding aldehydes. Also, it will do this type of oxidation also, alcohol and the sulfur getting intact, sulfur selenium getting intact here. There is a tempo, BIAB is used as a terminal oxidant, or we can say stoichiometric amount of BIAB is used to synthesize that the alcohol to their corresponding aldehydes. Similar is there also. Now let us talk about another particular unusual oxidant, that is the hypervalent iodine mediated oxidant. IBX is the O-iodoxybenzoic acid, is a mild reaction for oxidation of alcohol, and this is the structure of IBX. Here you can find that iodine having the hypervalent state. Okay, and this actually acts as a mild reagent, so it will do a secondary alcohol to their corresponding ketone. Now remember that tertiary alcohols are not getting oxidized in this process. Primary and secondary alcohol will actually go their corresponding aldehyde and ketone compound, because one alpha hydrogen is necessary for oxidation. Okay, similarly here also is the pyridine, and there is a one OH is there. This is the primary one. So in the presence of IBX and DMSO as a solvent here is used. So it will generate their corresponding aldehydes. Also, sometimes that what happened that here it is there. So sometime what happened that excess amount of IBX will lead to form a alpha beta unsaturated carbonyl compound from their corresponding saturated alcohol or carbonyl compound. For example, you can find here that this particular is the primary alcohol, and here IBX has been used in the excess amount. So instead it will converted this particular alcohol to their corresponding aldehyde, but also it will generate a alpha beta unsaturation here. Similarly, here in this particular example, you can find that this is only a carbonyl compound is there. 2 equivalent of IBX is used to generate alpha beta unsaturation here. Similar case here also, here both the secondary alcohol is there in a conjugate fashion. So in 6 equivalent of IBX, it is a huge amount of IBX has been used to generate their corresponding alpha beta unsaturated carbonyl compounds. So this particular part is very, very important, and you have to remember that part. So next we talk about another particular oxidative agent, that is the sodium hypochlorite. Now here we come the selectivity part. Like if you have both primary and secondary alcohol in your compound, and you want that specifically the secondary alcohol getting oxidized, then sodium hypochlorite has been used for that particular job. Sodium hypochlorite in acetic acid solution, it selectively oxidizes secondary alcohol to ketone in the presence of primary alcohols. Okay, so here you can find this is the primary alcohol and this is the secondary alcohol. So sodium hypochlorite is actually do selectively secondary alcohol oxidation over primary alcohol oxidation. So here the chemoselectivity is observed. For example, here you can also find that this is the secondary one, this is the primary one. In the presence of sodium hypochlorite, the secondary one getting oxidized and the primary one keep here. And in the second part is the protection of primary alcohol is there. So this particular primary alcohol getting protected. So if you don't know about the protection reproduction, you can definitely check my protection reproduction lecture series also. Here also second part, here only no, here also primary and secondary both the OH is there. So this is the primary alcohol, this is the secondary alcohol. So selectively secondary alcohol getting oxidized. Here also same, that the secondary one getting oxidized and primary one is no harm. Okay. Another selective secondary alcohol to ketone oxidation is there by using N-bromosuccinamide in aqueous condition. So NBS in aqueous condition selectively oxidize secondary alcohol in the presence of primary alcohols. So this is also a chemoselective reagent. Here also it is a primary alcohol and a secondary alcohol. NBS will do the secondary alcohol oxidation. Okay. However, some cases not only NBS can be used, direct bromines also used for the activated alcohol selective oxidation. So this will be, you have to remember. We start about oxidation of aldehydes to carboxylic acids. Okay. So first of all, this is aldehyde. This will undergo oxidation to get their corresponding carboxylic acid. And how it is oxidation? First, the oxygen is inserted here. That means it is oxidation. Also, here the carbon oxidation number is +1 and here in the carboxylic acid, the carbon oxidation number is +3. That means it will go +2 oxidation is happening here, aldehyde to carboxylic acid. Now let us understand that what is the methods that actually capable to do this type of oxidations. Okay, so penic oxidation is the most important oxidation pathway to do aldehyde to carboxylic acid oxidation. Then it is the KMNO4 is the vigorous oxidation observed. Then tolerance reagent is also useful for synthesizing aldehyde to their carboxylic acids. PDC in DMF, that is already discussed, and Jones oxidation in room temperature. These two are actually already discussed in our previous lectures. Okay, so now let us start about our discussion with penic oxidation. So sodium chloride, the NaClO2, it is actually called as the penic oxidation reactions. So sodium chloride is a mild, inexpensive and selective reagent for the oxidation of aldehydes to their corresponding carboxylic acid under ambient reaction condition. And this question is come in the NET also, NET exams. So this is the structure. Okay, now in presence of sodium chloride and there is a one acid H plus condenser is there, there is a sodium H2PO4 and 2-methyl-2-butene is used to synthesize this particular aldehyde to their corresponding carboxylic acid. Now in the reaction condition, you may find that what is the role of this 2-methyl-2-butene? Basically, this 2-methyl-2-butene is often incorporated as an additive and has been proposed to function as a scavenger of any electrophilic chlorine species. Here in this particular pathway, this is a HOCl generated in this particular reaction, and this particular question is come in the NET December 2023. So let us understand the mechanistic pathway first. So mechanism is that initially these two are actually combined to generate HClO2, this particular compound, and then this particular lone pair of aldehyde carbon will actually captures this particular proton here and it will generate this, and this particular acts as a nucleophile. So here the electrophilicity of this particular carbon center getting increased, so that this particular negative is attacks here and this particular one goes about to remove the positive charge from the oxygen here. After that, this particular oxygen lone pair will capture this hydrogen, this particular black hydrogen. Okay, so the color coded is here, so you can easily understand or follow. So this will there, and this actually bond will goes here, and the overall uh, this OCl bond breaks apart. So we got HOCl and our corresponding acid. And now this particular HOCl react with this 2-methyl 2-butene to scavenge to get this particular compound, and it will be out from the reaction mixture. So this is the typical mechanism of the Pinnick oxidation reactions. So let us talk about some examples. Example as already discussed, that here you can find this, the CHO is there, like aldehyde group is here, so it will convert it to their corresponding acids. Also in this particular reaction, here is the aldehyde. Okay, you don't have to bother about other functional groups here, just find the aldehydes here. So here it is aldehyde. In presence of Pinnick oxidation reaction condition, it will generate their corresponding acids. Okay, now let's talk about other reagent, that is the KMnO4, that is a potassium permanganate. Now potassium permanganate is a strong oxidizing agent, and its reactivity depends on whether it is in use in acid condition, neutral condition, and basic condition. So it has been found that in acid conditions, it is actually show vigorous oxidation, so it will transform aldehyde to their corresponding acids. And the Mn7 here, it's actually reduced to Mn2 in this particular reaction conditions. And in basic and neutral condition, MnO2 is usually formed, and we know that MnO2 has been used for oxidation of allylic, benzylic, and propoxylic alcohol, that I already discussed in the previous classes. Okay, so it is written here that this combination, this is a KMnO4H2SO4 in a water medium, is oxidized aldehyde and the corresponding carbonyl acid over a large pH range. Alcohol, alkenes, and other functional groups are also oxidized by potassium permanganate. That's why this particular method is not a chemoselective reactions. Okay, so this you have to remember. But in the case of Pinnick oxidation condition, this is chemoselective. But here KMnO4 is not that much chemoselective. Okay, now let's talk about Tollens reagent. This is silver oxide. Tollens reagent is used to synthesize aldehyde to their carboxylic acid derivatives, and is a very mild reaction conditions. So it's only able to synthesize aldehyde to carboxylic acid. So here you can find the different groups, functional groups are there, but it will actually do its job to synthesize aldehyde to their corresponding carboxylic acid. Similarly, here also here is a carboxylic acid. The aldehyde is present here. In presence of Tollens reagent condition, it will form carboxylic acids. Now let us talk about the pyridium dichromate. As I already discussed in our chromium based oxidation, that PDC in presence of DMF solvent, it will show direct alcohol to carboxylic acid because of the water content. They actually increase the reaction rate as well as the reactivity. So the non-conjugated aldehyde are readily oxidized in the corresponding carboxylic acid in good yield in DMF as a solvent. So this is our corresponding aldehydes. It actually PDC in DMF condition, it will move towards their acid part. Okay, and also as I discussed, that primary alcohol are oxidized to their corresponding carboxylic acid in good yields. So here this is the primary alcohol. It react with this particular PDC and DMF condition. As we know that DMF contains water, which actually accelerate the reactivity of PDC. So directly primary alcohol to acid conversion observed. Okay.
So suppose you have a CHO or RCO R dash, and you want to convert it their corresponding ester. Okay, so how can you do that particular thing? So in this particular class we will learn about that part only. So first we are talk about a reagent that is called Code Gilman Gammon oxidation. This particular reagent are actually, we can say, a cocktail of different reagent. The mixture as the manganese dioxide, NaCN and methanol. This mixture are actually called this Corey-Gilman Gammon oxidation, and this is a convenient method to convert unsaturated aldehydes directly to their corresponding methyl esters. Now, as we know that these reagents have their individual roles, like if you remember that manganese dioxide can be used to oxidize the allylic, propacylic or benzylic alcohol. NaCN is a good source of Cn minus, and methanol acts as a solvent as well as acts as a sometimes acts as a nucleophile and all, so that will be discussed. So let us understand this particular oxidation reaction by using a certain example. So here you can find this is a benzaldehyde. Now this particular benzaldehyde will convert to their corresponding esters by a set of reactions. So what happened that initially that particular benzaldehyde, and here in this particular reagent acetic acid acts as a solvent. So this particular acetic acid and sodium cyanide, these two are combined to form that hydrogen cyanide, which is a good Cn minus source. Now this Cn minus will actually attack the carbonyl carbon of this particular CHO group, which is a electropositive, to form this type of compound. Now if you carefully find, this particular OH now become a benzylic position OH, that benzylic OH. So in presence of MnO2, that particular benzylic position OH will convert to their corresponding carbonyl compound, and afterwards that ROH, that methanol or ethanol, it will actually react with the cyanide side. So one type of cyanide hydrolysis has been observed to form this particular compound. Okay. Now let us see certain example of this particular reagents. So for example, that I already discussed this. Okay, like MnO2 and sodium cyanide, methanol and acetic acid will lead this particular part, and this particular reagent is so versatile that here you can find that the chiral center present here, here also chiral center present. It doesn't affect the chiral center, but it will selectively oxidize that particular aldehyde to their corresponding methyl esters. So this is the versatility of this particular reaction and the selectivity. Now let us talk about, if you have ketone in presence of aldehyde and if you want to make esters or lactone, then how can you do? So in that particular case, there is a very famous name reaction is there, that is called the Weyer-Villiger oxidation. I hope that you are familiar with this particular Weyer-Villiger oxidation, where that Weyer-Villiger oxidation is a classic method for the oxidative conversion of ketones into the corresponding esters or lactone. Like if it is a open chain ketone, then it will form esters. If it is a ring ketone, then it will form lactone by oxygen insertion into acyl CC bond. That means this particular bond, oxygen getting insert between this to form the lactone. And what is the reagent used here? Reagent mostly used here is paracetic acids. Paracids such as the MCPBA, that is a metachloroparbenzoic acid, trifluoroparacetic acid, or normal paracetic acid. This type of reagent has been used to synthesize this type of ketone to lactone conversion and by the Weyer-Villiger oxidation. Now let us move to the mechanistic pathway of that particular reaction. So what is the mechanism? That initially your ketone is here, and this particular RCO3H, that is the par acid, it will form RCOO C double bond O minus. Now this particular O minus will attack in the electropositive carbonyl carbon center, which leads to this negative charge goes here, and now as we know that this will liberate a H plus, which can be captured by this particular carbonyl oxygen. Now we got this type of intermediate. Now if you see carefully, this particular oxygen is a del positive oxygen, because this particular are present in a conjugation. So this pull has been observed here, which leads to this particular oxygen is del positive. So that what happened, that when this OH will now again go to the ketone phase, this particular O is come back here, and this particular bond breaks apart, and the group is the mostly the larger group are actually migrate to that particular oxygen center, okay, which leads to eliminate this particular part, which the nothing but acetic acid, the RCO2H, okay, and to form the corresponding esters. Okay, now there is two thing that we have to learn, that why this particular is migrate over this. So that means there is a migratory amplitude is also there. So aryl group migrates in preference to methyl or primary alkyl groups, that you have to remember this thing. Typically the order of migration preference is tertiary over secondary over allyl over primary over methyl, and also the preference of the migration of the aryl group is when that particular aryl group has the electron donating group attached to it, that will show more migration over the particular aryl group which contains an electron withdrawing group. This thing we have to remember. Also the reactivity of that particular Baeyer-Villiger oxidation can be dependent onto the which type of per acid it has been used. Like if the trifluoroper-acetic acid is used, then the rate of that particular Baeyer-Villiger oxidation is much higher compared to third butoxide, third BuOOH, overall the H2O2 and the normal per-acetic acid. Okay, that means the more this pool, that means the more del positive nature of this particular oxygen center, which leads to the more faster reactivity of the Baeyer-Villiger oxidation. And I hope that this thing will be clear to you right now. Okay, now let us talk about another thing. Like suppose you have a ketone R, now you want to transform this to an acid. How can you do that? So typically there is no such reagent are there, but somehow that if it is a methyl ketone, then there a possibility to form this type of acid by using a test that is taught us in the class 11-12 or the BSc level, that is called the iodoform test, which actually detect whether that particular your compound contains methyl ketone or not. Okay, so as I already discussed, that if you have methyl ketone in presence of iodine and NaOH, it will form carboxylate ion and triiodomethane as a precipitate, that is a CHI3, and this is the yellow solid formation, which actually shows that yes, your compound contains a methyl ketone. So So other compounds are also show positive iodoform test like acetaldehyde, ethanol, secondary alcohol which contains methyl group in alpha position, isopropyl alcohol. This also give the positive result of iodoform test. But since we are talking about the oxidation of ketone to acid, so we are mainly restrict ourselves to this type of example. When it has the methyl ketone, then in presence of iodine and NaOH, we can prepare the carboxylate ion, which followed by water workup will get the corresponding carboxylic acid. Okay, so now let us see the particular mechanism of this particular transformation. So the transformation is this is the methyl ketone and this is the alpha carbon. Now in presence of NaOH, NaOH captures this particular H to form a negative charge here, which actually attacks the iodine to liberate a I minus, and this process is continued and all are reversible step, to be honest, till here where the Ci3 has been formed. Okay, and then the base attacks here, and now this particular Ci3 is a good leaving group. So when that particular own minus will actually backs there, Ci3 goes out, and then this Ci3 will capture this particular acidic hydrogen here to form the carboxylate ion, which has the counter ion of sodium from NaOH and iodoform. Like triiodomethane has been formed. It is the yellow color precipitate, and we generate our corresponding carboxylate ion from methyl ketone. So hello everyone, welcome back to another particular lecture of our reagent chemistry course, and this is class 32, and in this particular class we will mainly focus on the reagents which actually used to transform ketone to the alpha beta unsaturated ketone. That means imagine that this is your ketone compound and you want to transform this ketone to an alpha beta unsaturated ketone. That means you want to generate a unsaturation here. So what is the reagent? That will be discussed in this particular class. So basically there are two different type of reagent is there. One is the Segusa oxidation and another one is the selenation. So we'll discuss both. So first let us talk about the Segusa oxidation. Okay, Segusa oxidation, it is a two-step method to develop ketone to their corresponding alpha beta unsaturated ketone. And what is the reagent of this particular oxidation reaction? That is TMS chloride, base and palladium. Now if you see the reaction mechanism that we will discuss in the next slide, you will find that palladium 2 might be used in the stoichiometric amount, but the palladium 2 is very costly as well as it is a metal. So generally we tend to use this palladium 2 as a catalytic amount. So the scientists introduced some kind of terminal oxidant like oxygen, parabenzoquinone. This type of terminal oxidant has been used in the previous lectures where the OSO4 has been used, process dihydroxylation. They are also NMO used as a terminal oxidation. Similarly here, this palladium, if you use the palladium at a catalytic amount, we have to introduce some kind of terminal oxidant, because this particular reaction process, palladium 2, it goes to palladium 0, which is the active catalyst, which again return to the palladium 2. So do this particular transformation or to this type of catalytic cycle, we need some kind of terminal oxidant which can be used in a stoichiometric amount so that the palladium become the catalytic one. So here also that oxygen, parabenzoquinone, this type of terminal oxidant has been used, and this is very cheap compared to palladium. Okay. So let us see one example of Segusa oxidation and then we'll move to the mechanistic pathway. Okay, so here you can find this is your carbonyl compound, this is ketone, where this is the alpha position and this is the beta position. Similarly, this one is the alpha position, this one is the beta position, but this is little hindered over this is position. So always remember that this Segusa oxidation or selenium oxidation, they are tend to form alpha beta unsaturation where there is a less sterical hindered is observed. Okay, so here you can find that TMS chloride, that is one of the reagent, and base here lithium TMP has been used as a base, and the second step is the palladium 2 has been used in presence of acetonitrile solution to get our this type of compound. There is the alpha beta unsaturated ketone. Okay, now let us move to the mechanistic pathway. So this particular mechanism is involving, first is the silyl ether formation, and the second time is treatment with palladium 2, which actually nothing but a beta hydride elimination. So let us see the particular mechanism. So this is the step 1. Um, yeah, this is the step 1 where basically this particular carbonyl compound has been treated with the TMSCl and base to form silyl ether. How it is forming? You can see here, this is the alpha position which contains H, which is the acidic hydrogen. So base will capture this particular acidic hydrogen and then a negative charge is formed here. Okay, now this negative charge will go here, this will go here, so here O negative is formed, which actually attack in the TMS to remove that chloride, that we got the silyl ether. Okay, now this particular silyl ether in presence of palladium, okay, that palladium chelate with this particular double bond, chelate with the palladium, and it will form this type of intermediate, and they are in equilibrium. So when this particular intermediate is formed, now you can find here, this is your palladium center, here the alpha, this is the beta, and this particular hydrogen present here. Okay, this is the beta hydrogen. Now we know that palladium has the d field d orbital. So this particular d orbital actually attack the sigma star orbital of this particular hydrogen to get this type of beta hydride elimination, and thus we will get the corresponding desired product, that is the alpha beta unsaturated ketone compound. Okay, so now in the next segment we talk about the another reagent, that is a selenation. Selenation followed by oxidation followed by elimination. This is the main sequence of this particular reagent. Okay, the initial selenation of the particular carbonyl compound has been observed, followed by oxidation of selenium center and elimination. Here the reagent is PHACBr, that phenyl selenium bromide or phenyl selenium chloride. This can be used to selenate enolate of ketone, or ester, lactones, lactams, all are actually show this type of reactions. Okay, so let us see one example. As I already discussed in the previous segment, that mostly that particular alpha beta unsaturation has been observed in the lesser hindered site over this case. So we observe this is our starting material, and we observe this type of alpha beta unsaturated ketone. So why what is happening in between? Let us see. Initially that LDA THF will form enolate as expected, and that particular, in the case of enolate where the TMSCl, in presence of TMSCl, that oxygen center attacked in the particular TMS to form OTMS, but here that carbon center attack in the selenium to form the selenate enolates. So why it is happening, we'll learn in the enolate chemistry part, enolate chemistry courses, because of the hard enolate soft enolate concept is there, so we'll discuss there. heart center, soft center. Okay, so remember that in this particular cases, although it is forming enolate, so the negative charge will actually attack here to remove the bromine to form this type of selenate enolate, and then this selenate enolate will first uh, oxidation, and the second is the elimination takes place to form this type of alpha beta unsaturated ketone. Now let us see the actual mechanism of this particular reaction. And also common oxidants like hydrogen peroxide, ozone can be used to perform the syn elimination. Please remember that this is the syn elimination pathway has been followed. Now let us see the mechanistic pathway. Like initially, as I already discussed, that it will form enolate, then this particular enolate comes back and it will attack here, and bromine goes out to get our this particular selenate compound. Now in presence of oxidizing agent, like for example H2O2, this will actually oxidize the selenium center to form this type of product, which now undergo syn elimination pathway to form the corresponding alpha beta unsaturated carbonyl compound, and the byproduct is PHACOH. Okay, now let us go drift a little bit different step, where suppose you have a alkene and now you want to form allylic alcohol. Now what should be the reagent there? The reagent is ACO2, that's selenium dioxide. That selenium dioxide can be used for oxidizing alkenes to their allylic alcohol. And terminal oxidant was used while using catalytic ACO2, that I already discussed in the previous segment. Okay, so what is the mechanism of this particular part? See, first a in reaction has been observed where this particular allylic hydrogen are actually captured by a ring concerted manner to form the allylic selenic acid. Okay, now if you see this particular intermediate closely, you can find that 1 1 2 2 3. That means here a 2 3 sigmatropic shift reaction has been observed here, where this particular bond breaks apart and this particular bond is forming. So after 2 3 sigmatropic shift, we got this compound, which in the water workup or quenching, we got our final allylic alcohol product and ACOH whole 2 as a byproduct. Now this ACOH whole 2 in presence of terminal oxidant, it will form ACO2, which again go to the reaction mixture and do that particular reaction. So this is the oxidation of alkenes to allylic alcohols. Now there is another interesting thing in presence of ACO2 type of reaction, but before that we will see what is written here. That mechanism involve in reaction followed by 2+3 cycloaddition or sigmatropic reagent, we can say, and also oxidation typically occurred in the more highly substituted terminus of the alkene. Now if you have a carbonyl compound, if we treat that type of carbonyl compound in presence of ACO2, it will show dicarbonyl compound, where that particular alpha carbon is getting oxidized. This is alpha carbon, this is alpha carbon. In presence of ACO2, this particular alpha carbon getting oxidized. Similarly, when we treat with acetone, this particular alpha carbon is getting oxidized to form this type of product. And similarly also this type of non-borrowing system, so the same thing has been observed. And also ACO2 oxidize the benzylic position also. That means if you treat toluene with ACO2, you will find a benzaldehyde. And this is the last lecture of our reagent chemistry course, where we will discuss about oxidative cleavage. Now oxidative cleavage says that if you have this type of carbon-carbon bond, you will to cleave this particular carbon-carbon bond by oxidatively by using certain reagent, and in this particular class we talk about those reagents. But before that we have to learn that the definition of oxidative cleavage. So the oxidative cleavage is a chemical reaction where a double or triple bond in an organic molecule is broken and the molecule is split into smaller fragments. That means we are just splitting that carbon-carbon bond by using oxidative pathway. Now in this particular case you have to learn two type of oxidative cleavage that is very useful, as well as in exam point of view that is very important. That is the oxidative cleavage of diols and oxidative cleavage of alkenes. Diols suggest that you have this type of compound and you want to break this particular carbon-carbon bond, and alkene we know that this particular bond breaking. So in case of oxidative cleavage of diols, there is two famous reagent has been used. One is the NaIO4 and another is a PbOSe whole 4. These two reagent has been used to break this type of diol. Okay, and in the case of alkene, there is a three different reagent. The one is the O3, that ozone that breaks that particular alkene bond via ozonolysis. We'll discuss that, as well as the two name reaction is there, Leminax-Johnson oxidation and Leminax-von Rudolph oxidation. So these two we'll discuss in this particular class. First, we talk about the oxidative cleavage of diols. Oxidative cleavage of diols, sodium periodate or H5IO6 can be used to cleave vicinal diols into two carbonyl compound or into a single compound with two carbonyl groups. That means if it is a open chain type of compound, then it form two different compounds, and if it is a single cyclic type of compound, then it will form a single compound with a two carbonyl group that we'll discuss in the particular examples. Okay, so now you can imagine that this is your 1,2 diol and this particular bond will be broken. So what happened that NaIO4, it will form this type of 5-member cyclic ring, and after that this particular cyclic ring breaks and it will form this type of this particular carbon-carbon bond breaks and we got two carbonyl groups here. Similarly, in the case of trans diol, it may be possible to do this type of transition state if those are close enough or there is a lesser steric hindrances there. But however, in the case of cis product, the reaction rate will be much higher over the trans. Okay. Now let us talk about another example, that NaIO4, it can cleave 1,2 dicarbonyls. That means if you have this type of compound, there is a 1,2 dicarbonyl present here, then it will break this bond also and will form two different carboxylic acid group. Similarly, if you have this type of combination, then NaIO4 breaks this particular part, so we got a corresponding acid part here, and this will form the carbon dioxide and H plus is formed. However, there is certain limitation while using sodium periodate, that is that I already discussed about in the previous slide, that in the case of trans it might be possible to break this way because somehow it might get adjusted to form this type of 5-member cyclic ring and then it will get broken. But in the case of this particular compound, if we draw it like a transdecalin format, then you can find one OH is here and one OH is here. That means there is no possibility to form the 5-member cyclic ring here. So that means this type of compound, this particular bond will never be broken by using NaIO4. Now let's talk about another particular reagent, that is lead tetraacetate, that means PbOSe whole 4. This is also a common reagent for the cleavage of diols. However, it is a strong oxidant and can react with a variety of functional groups. For example, you can find here, this is a D-mannitol. Yes, this is a protected form of D-mannitol. Now this particular D-mannitol, here you can see the 2 chiral center has been there. Now treated with the lead tetraacetate, we successfully cleave that particular bond and we form this type of chiral compound, and this is very important uh, starting material for a different natural product synthesis. Okay, and this lead tetraacetate also uh, do this type of cleaving by 5-member ring. Also it can be react via the stepwise manner. For example, in the previous case I have told you that this type of compound cannot be cleaved, that particular CC bond cannot be cleaved by the NaIO4, but it can cleave via PbOSe. How? Because PbOSe is actually coordinating with this, and it liberate one OSC minus. That particular OSC minus captures this proton and generate a O negative here. Then O negative come here, these bonds cleave and this will go out. So this particular compound cannot be oxidative CC bond cleaved by NaIO4, but it can cleave via PbOSc whole 4. This is the reaction. Okay, now we are done with this particular 1,2-diol. Now let us talk about the oxidative cleavage of alkene by ozonolysis. I hope that ozonolysis reaction you are familiar with this, because the ozone is the widely used reagent for the oxidative cleavage of olefin, and the particular reaction is considered to be 3+2 cycloaddition of oxygen into the alkene. Now let's dive into the mechanistic pathway of this particular reaction. Initially, this is the structure of ozone. Now this ozone react with the corresponding alkene via 3+2 cycloaddition. That means this particular negative will actually initially attack here, and then this double bond attacks here, and this particular oxygen is electrophilic, so this particular bond will go there and to form this intermediate. Now this intermediate called as the mole ozonide. Now here if you see that there is a 2 OO bond is there. Okay, now we know that hetero bonds are not that much stable over the CC bond, so this intermediate is unstable, so that it actually breaks apart. How it is breaks apart? That this particular lone pair goes here, this goes down there, and this is back to form this type of 2 different intermediate in situ. That is called as a carbonyl oxide. Now these 2 intermediate are actually tends to rearrange to form ozonide, which is much stable over mole ozonide. How? That this particular negative actually attacks in this particular carbonyl carbon center, this goes up. Okay, so we'll discuss in the next slide. Here you can see that this negative charge actually attacks here, and this goes up. This negative will actually attack in this particular carbon center. The driving force is to stabilize that particular oxygen center to form this particular ozonide. Now when we generate that particular ozonide, now you have variety of option that what you want as your final product. By working different reactive workup condition, you can might generate a carbonyl, might generate a alcohol, might generate an acid compound. Okay, now if you treat that particular ozonide with reductive workup by using dimethyl sulfide or iodine or triphenyl phosphane zinc acetate, then it will show a reductive workup and you will obtain the final carbonyl compound, that is a ketone compound. Okay, ketone or aldehyde compound. However, if you if you want to go direct alcohol stage, then you have to do a reductive workup by using lithium aluminum hydrate or sodium borohydrate. That means a hydrate donator is required to form ozonide to their corresponding alcohol. And if you want an oxidative workup to get ketone or carboxylic acid, then you have to treat that particular ozonide with H2O2, Ag2O, there is a silver oxide, CrO3, KMnO4 or O2. That means the oxidative agent has been required to do that type of oxidative workup to get ketone or carboxylic acid. Now let us see certain example of that particular reaction. For example, you can find here, this is ozone and this is the starting material. Obviously, ozone will react with this double bond to form ozonide. Initially it will form mole ozonide, followed by it will form ozonide via rearrangement. After that you can see there is a H2O2 is there. H2O2, when you see H2O2, the reaction that clicked in your mind that it is doing a oxidative workup. See here, oxidative workup H2O2. That means at the end product it will form either ketone or carboxylic acid. Now as expected it will form a ketone because here is a no chance to form the carboxylic acid. However, in this particular part we will form the carboxylic acid. Similarly, for this particular reaction, you can find here that in presence of O3 it will also form mole ozonide, then ozonide. After that you can see here the reductive workup is doing, that is the dimethyl sulfide has been used. That means it will form a carbonyl compound. Like here it will form a O, that is a ketone, and here it will form a acetaldehyde, aldehyde. Okay, now let us move to the two named reaction where the oxidative cleavage of alkane has been observed. First one is the Laminex-Johansson oxidation. It is a two-step oxidative cleavage method where the reagent has been used is the catalytic OSO4 and stoichiometric NaIO4. And how it is two-step? Because in presence of catalytic OSO4, that alkene is converted to 1,2-diol and followed by treating with the NaIO4, it will form the corresponding that CC bond cleavage takes place. Okay, here actually NaIO4 has dual role in this particular reaction. The first is obviously breaking the carbon-carbon bond, and if you remember about the OSO4 based cis dihydroxylation formation that I already discussed in I think class 19 or 20. So here you can find that during the course of reaction OS8 are actually converted to OS6, and this OS6 are not the active catalyst, so it requires a terminal oxidant to return back OS8. So NaIO4 actually acts here as a terminal oxidant, so that actually that OSO4 has been used here in the catalytic amount and NaIO4 has been used as stoichiometric amount. Okay, and this is a fair alternative of O3 base cleavage. So this is the reaction you can find here, that this is the alkene react with the catalytic OSO4 in room temperature to form the dihydroxylation, the diol formation takes place, and followed by NaIO4 treatment we got this particular CC bond cleaved. Okay, and you can find here that this all are reaction in the room temperature reaction, where in the case of ozone we have to do a lower temperature reaction. So it is a fair alternative of the O3 base cleavage. However, this particular reaction also have a drawback. Since it reacts use the OSO4, OSO4 is practically toxic and volatile. Okay, that's why to eliminate the OSO4, there is a upgradation of this particular reaction has been introduced, that is the Lemieux von Rudolph oxidation, where they actually throw down the OSO4 and bring that KMNO4. KMNO4 is also acts as a dihydroxylation formation, the diol formation, and the similar mechanism has been observed. And interestingly, this reagent condition, because KMNO4 is also a oxidant here, so the final product formation is acid, and in the case of the previous one, you can find a carbonyl compound here, but in the case of this Lemieux von Rudolph oxidation, you will form acid over aldehyde as a final product. So for a simple example, you can find here, this is the most classical example that I have found in the book. So here you can find there is the alkene is there. Now in presence of Lemieux von Rudolph oxidation condition, that is NaIO4 stoichiometric and KMNO4 catalytic amount, the final product is the acid. Whereas in the Lemieux-Johnson oxidation condition, where the OSO4 and NaIO4 combination has been used, the final product is aldehyde. So with this, we have to officially end the reagent chemistry course. I hope that you will learn a lot in this particular course, and that's all from here, and then we'll discuss about some kind of reactions and examples of this particular topic. So thank you.